Cool. Welcome to Rust Nation. I am introducing our speaker. But yeah, this is the first talk of the day, or I guess second. And yeah, we have Ida. She currently works at Meta and does a lot of Rust and C++ interop. So we're getting a very exciting talk on Rust and C++ interop. I'm pretty sure you, like me, don't know that much about it, so this should be a great talk. Cool. All yours.
This is scary, but yeah, my name is Aida. I'm a software engineer at Facebook, Meta now. I joined when it was Facebook still. Yeah, and I'm gonna talk today about the asynchronous Rust C++ interop. So thank you for coming today, this early in the morning. I appreciate it a lot. And just a quick intro into the inspiration for this topic. My journey with Rust started like 4 years ago when I worked in source control team and started working on the source control server. That was one of the first projects within Meta written on Rust, and one, I guess, the main successful one in my opinion. But yeah, so throughout my journey in the Rust and source control, sorry. Oh yeah, it works now. So I had a project where I had to write bindings for my SQL client. The reason was that Rust, being a relatively new language within Meta, didn't have like a lot of support from like different clients that we needed to in order to communicate to databases or like other services. So there's a decision made to write a thin wrapper around the official MySQL C++ client within the company. And that was the project I worked on. I had a lot of ups and downs within this project. And hello? Let's try again. Hello? Yeah. So, yeah, and spending several hours, not several hours, I guess several days and many hours of debugging different issues, that's what inspired me to talk about asynchronous interop within C++ and Rust. So, going to the agenda for today's topic. So, we're gonna briefly talk about general C++ Rust interoperability and the ways you can do that. Then we're gonna look at some examples of Rust bindings for C++ using CXX tool library. Then we're going to talk about the problems within asynchronous programming between Rust and C++. Hello? Okay. Yeah, then we're going to look at how to run asynchronous C++ code from Rust. And then we're going to delve into the different issues that you can encounter while doing asynchronous interop. Okay, so just briefly talk about the motivation. Why do you want to write bindings for C++ code? You may want to rewrite the whole project into Rust. That's one of the options. But usually you may not have enough resources. The library that you want to use has a unique set of features, and rewriting doesn't always resolve the existing issues. It most probably will bring more issues, and you probably don't want to spend time on that. If you work like in a company where like you own the C++ piece of code, it probably can be well supported, well maintained, still in the process of active development. These are all the like reasons you can opt into write bindings instead of like your own Rust solution. Cool. So how can we bind C++ and Rust together? So there's a few different tools that you can use in order to write bindings in between C++ and Rust. The oldest and I guess the most popular one being the bindgen. This is in a way, very low-level tool, but also a bit of a high level, because on the one hand, it basically generates a lot of unsafe extern code for Rust, but like it's kind of high level because it can basically go through the whole libraries of code, like different like chunks of header files, and operate at the best effort, basically trying to create as many bindings as it can, generate as much code as it can, not to fall if something goes wrong. Now the CXX tool is a new one, kind of new. I mean, it's several years old now, but still newish. The approach of CXX is to create fast and safe bindings in between C++ and Rust. It kind of works both ways. And it tries to support more of like seamless translation between more complex data structures like vectors, strings, or smart pointers, which is very, very important. Yeah, now let's look at how both of these tools work. In general, not like diving too much into details. Also, just to let you know, there are other tools that you can use, like for example, CPP. I have not tried that much of like using that tool, but and it's going to be outside of the scope for this topic. But I'm pretty sure it's going to be like the issue is going to be pretty much the same everywhere. Cool. So bindgen. So the idea for bindgen, again, is to feed it a bunch of header files, configure the ones that you want to use, or like feed it a whole library, configure the header files from this library you want to use, and yeah, and run the compilation, generate Rust external C code, and use it from Rust. Nice and simple, but not so much. So bindgen, and not only bindgen, and pretty much all the tools that try to create bindings, they cannot be too smart because the C++ code is very complex. There can be lots of like inheritance things, like lots of templates. Well, the code is quite complex, and the tool tries to understand it as best as it can, but it cannot really understand everything. So there's some limitation that you could like that the bindgen cannot go through, and not only bindgen but other tools as well. So in order to kind of like bypass these issues, usually you create a simplified API for on top of the library you want to expose. It could be like, I don't know, hiding all the different templating and stuff like that, trying to wrap it in like more of a simplified C-like structures and functions, and then try to expose those ones into Rust. Then you try to configure bindgen because you have to provide the allow list of files you want to generate, because if you're gonna just, hey, this is the library, just go through it, it may generate different weird things, and you may not like it. So you have to disable some parts of that to not cause any errors, and like import basically the stuff that you need. And it, as I said before, it's going to generate the kind of low-level, unsafe Rust external C code that you can use from the Rust code. Now, the CXX is a bit different approach. So the idea of CXX, in a way, is kind of more low-level than bindgen because it doesn't operate kind of like on the huge chunks of C++ code. You have to kind of manually set up the bridge, the API between two languages, and generate the bindings from there. So this kind of like setup called bridge, and it allows you like a two-way road in between two languages. It allows you to define shared types that are going to be natively translated both to C++ and to Rust. It allows you to specify types you want to expose, functions, and methods. It also are quite limited in a understanding of templates and stuff, and you can also opt into writing your simplified version of the library you want to expose. But in general, the idea of the CXX library is to provide you more controlled environment and like a safe environment. Like for example, the function, like the bridge that you're writing, it's basically in blocks of external code, external C and external Rust code that contain not unsafe code, but actually safe. So it tries to employ static code analysis to check that the signatures of the functions are pretty much correct, And yeah, and the rest on you. So it makes basically your Rust code to be more convenient, less unsafe code, and it also, like the best feature, I guess, provides a smart pointers and like slightly more complex data structures. You don't want to mess up with row pointers. Now, so just to reiterate, so this is more of like downsides of one tool, or like why you could opt into choosing like CXX on top of BindGen if you would like to write your bindings now, for example. So BindGen operating on the best effort only can actually be a bad thing because it generates a lot of silent errors. So if you write in Rust, you know that there's kind of like an idea of like, if it compiles, it works. Well, if it compiles, it doesn't necessarily work in this case. And you don't want to go into the trouble in runtime. So another thing, lots of unsafe code. You may not want to have another API layer on top of the already created bindings where you have to rub all this unsafe code into the safe functions. So that may not be the great one. And one of the trickiest part is the huge amount of raw pointers. Basically because it doesn't allow you to seamlessly translate the smart pointers from C++, and the BindGen doesn't really know how to work with like ABI for like unique or shared pointers and translate them into Rust raw pointers. It's really hard. You have to watch the memory yourself. Now, in CXX, it tries to provide, as I said before, the safe API both ways to C++ and to Rust, and it supports smart pointers, which is amazing. Cool. Now, let's look at one of the examples. I will like reference this example throughout my presentation. It's going to be like a very simple library that we'll try to create bindings for. We're not actually going to create bindings, but like we'll see. So, okay, well, runtime issues. Cool. So this is a very, very simple API for like how your like database or MySQL client can look like. So we have a MySQL client class that like we set up using the address of our database, the shard, and it has like a very simple constructor, destructor, the one main function that allows you to connect to the database, and most importantly, it returns a future. It is an asynchronous function. Now, the connection itself is just like, well, a connection. It may have lots of like private parts. And the main method for the connection is a querying to the database, basically. Yeah, just for the simplicity, it just returns a vector of strings. Yeah, we don't really care at this point. So cool. Now, let's see how the generation of bindings works, for example, within CXX. It's just to give you an idea how it looks like and why it can be like a nice way to work with the bindings. As I told you before, there is a way to provide, like, for example, the shared structures or shared code in between C++ and Rust. And CXX provides you like a two-way bridge in between languages. This is like the example why it's a two-way bridge. So here we see like a part of the code that is CXX bridge. This is a Rust code, as you can see. And within the code, you can basically declare all the types you want to use within both languages. So here we just have like a very simple struct called studs. It has like a one string field and one like all integer field. Now, what we can see from Rust side is just like a simple, well, Rust structure. It's still like, it was defined in a Rust code. It is a Rust code. So it's just like normal usage for Rust, right? Now, how it's going to look like for C++, which is more interesting because we're writing bridge in Rust. So the CXX is going to generate you a header file for the C++ code. Here you can see the stat structs in C++, and it has a Rust string and also integer, like for another field, for the count field. That's basically the way it represents for like C++ code. Then the actual C++ code that you may write you can just use it as a normal C++ structure, nothing complicated. It's a native code, safe to use. Cool. Now, what if we want to come back to our example with MySQL client library and expose not like a shared structures, which are quite simple, but more complex ways with different fields, methods. So basically Rust may not know the size of the structures, the way it organized in memory, stuff like that. So as we can see, for the bridge, we can define a external C block of code, declaring the type that we want to expose, basically says the CXX in the compiler that, hey, this is the structure, the type that we want to see in Rust. It's an opaque type, meaning that Rust doesn't know the insides of it, it doesn't know the size, it doesn't know how it's structured. It's just like a blob of data, nothing else, just a blob. As you can see, you can also expose the functions and the methods. So you can expose the method, the connect we talked about. Currently, for simplicity, is just like a synchronous connect code. And it takes self. The methods within the external C code, they start with the self and as an argument, and they attribute to the type exposed within this code. So yeah, and for the constructor, because it's not that obvious to run the constructor, like to translate constructors, we kind of have a very thin layer of a API on top that's just do new MySQL client, it calls the constructor for the MySQL client and returns back to Rust. As you can see, we use the shared pointers and unique pointers here. This is the types that provide CXX as a seamless translation between C++, smart pointers, and Rust. And on the left, you can see the Rust code, where you can see that we just have a very thin wrapper around the MySQL client, and we just can create the normal Rust constructor, no unsafe code, very nice and smooth. We just call the FFI function, and that's it. Cool. Okay. Now, what is going to happen if we try to do asynchronous code? So we have this function connect. It takes client, it takes some options for the connecting, but it is future. By the way, I'm using the Folly here for an example for C++ code. You can use whatever library you want for asynchronous code. It doesn't really matter, but here we go. And yeah, so why is it complicated that asynchronous code is not the same as synchronous one? Well, the reason is because the function call, asynchronous function call is not the same as normal function call. Function call will return you a value. Asynchronous function call is not a value, it's a promise of a value. This is a container where the value will appear at some point of time, but you don't know when. And given the Folly executor, so basically calling the function will schedule a task that will be executed at some point of time, but you don't know when. It starts executing at the time of the calling of the function, but you don't know when it's going to finish. It may go to the server, it may be milliseconds, seconds. You don't really know. And as soon as the result is ready, the promised value actually fulfilled, and now you have the value itself. So in contrast to C++ asynchronous code, the Rust code works a bit differently. So here I'm using also Tokyo as a library for asynchronous programming. Again, you can use whatever library you want to, doesn't really matter. But here we go. So Rust features, in a way, similar, but there is an interesting difference. So basically, whenever you call a function, it doesn't really promise you anything just yet. So basically, calling a function doesn't start the execution. It doesn't schedule a task because, well, it's just, you just created a future object. It's like nothing else. Unless you actually poll the future, poll this, object, it's not going to execute anything. So that's one difference. And you can see, so at the point where you await on the future, this is when it actually starts polling and checking whether the value is ready or not, and will await until it's ready. So you can see that for the C++ timeline, the starting of the execution is the same as the function call. For the Rust, the start of the execution is when the await happens. You don't necessarily need to await. You can pin the future, poll it once, and see how it goes. Yeah, but just in general to keep in mind, it doesn't really schedule anything. So how do we bind two executors together? So from C++, from Rust point of view, we just want to call a function and get the result back. Yeah, we do want it to be asynchronous. We may have like a very like read-heavy or IO-heavy service. We do need to have a asynchronous ability to run code. So how does the Rust executor, Rust runtime, understand when the C++ runtime is ready to return the value? This is a good kind of question. So let's start just from the very beginning. How would you just schedule the future? Let's just like start the execution. So using any tool you want, like bindgen or CXX, you can generate the bindings. You can expose the function you want to use, right? The thing is, we cannot just run a synchronous call. Like it's not, like Rust doesn't understand the asynchronous like function. You can expose all the like futures and stuff like that, but it may be like too tedious to do. So let's just like say that because the futures start executing the time of the call, we can just do a synchronous call to the C++ and start the execution. So basically on the Rust side, we have a normal FFI call that is synchronous. Oh, nice. This FFI call contains within itself the call to a synchronous function to C++. And as I said before, it starts the execution. Yeah, and it returns the handle back to to the Rust side. So now we have a future that runs on C++ executor, and it will like complete in some amount of time. Again, a known amount of time. So how do you get the result back? That's quite a question, because on the Rust side, again, we want to make it native and safe and asynchronous. Cool. One way is to just expose everything. So we have a future that returned back to Rust. We can poll on future, nag it every now and then. Hey, are you ready now? Nope. We'll wait another second. Are you ready now? Nope. Let's wait again. And we have this very interesting loop, very boring, honestly. And as you can see on the right side, basically the future is the container that as soon as it gets fulfilled, we basically get the value back because it's ready now, right? Is it really asynchronous? Yeah, I doubt it. It's not really asynchronous. We have to just like constantly go through it. Well, I mean, we may sleep asynchronously, but like, it's not really nice and it's not sound. Cool. So how else can we get the value? So let's think about the maybe parts of our computer science education or something. So how the inter-process communication works, basically, or like, for example, a problem of ping pong between two processes. The way that things can communicate to each other is, for example, through the channel. So we can send letters to each other. The same thing here. We have two different runtimes that kind of like concurrently execute something and they don't communicate. So let's make them communicate. So let's create a channel between these two things and make Rust or C++ runtime to send the value back as soon as it's ready. So this way, from the Rust perspective, we just don't do anything. We're not constantly checking the future. We're just waiting on the channel to be fulfilled, to receive the message. And as you know, the channels in Rust, they can be asynchronous. So we can asynchronously wait on the message received from C++ side. So how does it actually work? This is a bit more complicated. So again, there is a thing called one-shot channel. That's basically like a way of sending a singular message in between two, like threads, tasks, whatever. This is a asynchronous. This is a asynchronous channel. So basically, the writes and reads for the channel. The writes from the reads from the channel will be asynchronous, so you don't have to like block on that. So let's see how it may go. So like we create the channel, right? We do call the function that schedules a task within C++ code and start the execution. Cool. The thing that we have to keep in mind is that we need to tell C++ code that this is the channel, you have to use this channel in order to send the message back. This is where the CXX way of translating both ways work really nicely, because you basically can like say, hey, this is like functions, actually not even like CXX, like Bindgen can do that as well. So basically you generate a simple kind of like bindings for the callbacks that that you can pass from Rust code to C++, and C++ will just call these callbacks, call these functions, and they will write you the result in the channel. You may expose again all the functions and methods of the channel. You don't want to probably do that. So for now, just like let's see the runtime. So we do pass the channel through to the C++ code. The future starts the execution. Then as soon as it's complete, it returns the result back. Now, what happens on the Rust side? So C++ is quite straightforward. But on the Rust side, basically, the first call to the future is a synchronous call. So Rust doesn't really know about anything async happening at this time, right? Now, at the point when we do await on the channel, that's when the asynchronous part starts. So as you can see, this is the asynchronous code, and as soon as it's ready, we have the value back. Cool. Now, more boring stuff. How do we actually execute that? So as I said before, like C++ have to know how to talk to the channel. This way we can use the callbacks, basically. So you can see like the transmitter is the just a like box, like a pointer to the sender part of the channel, and the result payload is going to be connection because we're trying to connect. And as you can see, it's a result because so C++ function can throw exceptions, right? We don't know how to interpret exceptions within Rust, so we may want to send them through the channel the same way as we send the actual result. So just having two callbacks, one for the fail and one for the OK result. So like within Rust, the reference is like minimal. It's just the result is going to be just the result, structure result of a connection and string as an error type. And we're going to provide two functions, two callbacks, one for the OK result and one from the fail result. And that's it. Rust code will be responsible for sending stuff over the channel, and C++ code will be responsible only for sending this stuff over the channel, or only for calling this functions from the channel. So this is how your connect function within Rust code would look like. Again, nice and smooth. Like you only have to do connect and wait, and then and not actually wait, it's just a synchronous call, and then you have to wait on the channel itself. Cool. Now that's it. They have lived happily ever after. Oh no, because it's C++. What did you expect? So yeah, it's not that easy. It's C++ code. Honestly, the only time I got segfault in Rust was when I did bindings for C++. So that says a lot. First issue that we may encounter while doing asynchronous code within Rust and C++ is the thread safety. So Rust has two kind of like simple and at the same time complicated concepts for the thread safety, for object thread safety. It's a send and sync traits. So send trait says compiler that this object is safe to send through, like from one thread to another, and sync trait says that it is safe to share the object in between threads. This is very important. Not all the objects can be sync. Like for example, if it's not thread safe, if you don't want to have concurrency errors, you cannot have sync implemented on your objects. So by default, for your complex structures and objects, the send and sync traits are not implemented. So you have to specify and declare it explicitly yourself that this is the trait, that this object is sync safe or is send safe. Yeah, and if you're not gonna, for example, if you do not implement these traits for your project, for your object, you cannot really run some of the asynchronous patterns of the code you may want to use. Like for example, sometimes you want to run the future, but kind of like spawn it on another thread, like maybe like, yeah, I want this feature, but I don't care whether it's going to execute on this thread or whether it's going to execute on another thread. So that requires send. You cannot just like send the feature to another thread and expect that non-send type is going to be fine with it. No, it's compilation error. So what's going to happen if we want to use C++ opaque types within this asynchronous environment? This is interesting because, again, the asynchronous patterns within Rust sometimes require you to have send and sync implemented. However, you don't necessarily know whether the type from C++ is actually safe to do that. So this is a good example because sometimes it can be easy to just copy-paste stuff, and quite frequently you do implement both traits at the same time for the objects because, oh, well, you know that this is like send and sync safe. For example, here, like we do like, okay, so connection send safe and connection sync safe. Or is it? We don't really know. Like, I doubt that connection is sync safe because this is a kind of uniquely owned object. You don't want the threads to mess up with that. And the issue within the bindings is actually that the engineer is responsible for understanding whether the type they're exposing is safe or not to send or sync. So basically, whenever you incorrectly declare things, you may run into the trouble. Like, for example, if you sync connection and then write a pattern, we're gonna, for some reason, use object within several threads, it's not going to be safe. You have like lots of concurrency issues, stuff like that. Another fun fact, I once saw an example of a person implementing the both traits for an object, not because they wanted to say that this is safe to use, but because they thought that unsafe keyword means that, okay, this is not safe to use. So they basically try to say compiler, okay, no, you don't have to send and sync that. But well, yeah, lost in translation, I guess. Okay, cool. So next issue, lost pointers. Okay, that's one of the things one of the reasons you don't want to use raw pointers, but you may have to use raw pointers if you use bindgen, or if for some reason you cannot like send smart pointer over like from the C++. Like for example, the function you're trying to call returns you a raw pointer. You may want to wrap it in a like unique pointer or something, but if you necessarily, like you have to just send a raw pointer. This is the thing that you have to be aware of. So, first thing is we have a connection on C++ side. It's a pointer. We write it to the channel and we try to receive it on the Rust side. Cool. What if, for some reason, the channel, the receiver part of the channel drops out? What if, like Rust, okay, I don't need this connection anymore. What happens next? Well, nothing good. The connection is actually leaked. You don't know where the connection went to. So usually when the receiver drops, the receiver drops, the stuff within the channel is going to be deconstructed, so it's going to be destroyed. However, Rust doesn't know anything about the connection. From the Rust perspective, connection is the opaque type. We don't know the size, we don't know anything, it's just a pointer to some part of the memory. Well, pointer is just like, well, integer. So yeah, it's gonna be destroyed, but the memory itself is not gonna be destroyed. It's still gonna be occupied. So it's like, first of all, it's memory leak, which is not great. So, second of all, you can have deadlocks. So let's see this particular example that I actually ran into, not in this particular setting, but it was pretty similar. So what if we have connection pool? For MySQL, connection pool is basically a way to have multiple connections to the database at the same time and reuse those connections. They have usually expiration time, so basically you create connection, it leaves for like 5-10 seconds, whatever you set up it to leave for, and it's gonna destroy it, and then you get another connection. So basically the way to save up on the round trips to the database to connect every time. So cool, we have connection pool set only for 2 connections. Now, what if we try to connect twice and then the third time? So basically timeout 5 will mean like that we're gonna like set up 5 milliseconds timeout for the connection asynchronous function to implement. What if we have delays within the trip to the database? What if something is like wrong and it's not gonna finish within 5 seconds? What's gonna happen? Oh well, the Rust part, the timeout part is like, okay, the time is up. I'm gonna drop this future, I'm gonna drop this receiver part of the future, because this is where our synchronous code lies, right? And I'm gonna forget about that. The same happens for connection B, or for the second connection. We call the connect again, we wait 5 milliseconds, it doesn't return back, we interrupt the future, we drop the channel and everything within it. Cool. So what's gonna happen next? So both pointers are gonna be leaked. And when we do the connection, it's gonna stuck. Why? Because the connection pool is busy. Because none of the connections were destroyed. They leaked and they're not actually freed. So the connection pool thinks that both connections are in use. They may be destroyed at some point of the future because like expiration time for the connection. So yeah, they may be destroyed, but you may wait for like, I don't know, 10 seconds, 5 minutes sometimes. You don't want to do that, right? So how can you avoid that? So there are two things, like within CXX, you can use smart pointers. You basically can wrap it up in a unique pointer and send it back to the Rust. That will ensure you the safety of deconstructing things. So unique pointer has a deconstructor in it, so it's gonna be a seamless translation. When the channel is gonna drop, unique pointer is gonna be destroyed and the connection memory is gonna be freed. Now, bindgen doesn't allow you to have unique pointers, but you can work around that using a wrapper function and calling the destructor yourself. So basically here you're gonna expose the constructor within the free connection kind of like function, C++ function, where you have to call delete on the function or delete on the object. And this way, Rust will know that you can, like whenever the object is destroyed, it's gonna call the free connection function and it's gonna drop the C++ memory, the object memory. Cool. The other issue, lifetime issues. And no, it's not Rust getting old. Although it's also maybe an issue. But okay, what's gonna happen if a C++ object uses Rust object? As you know, Rust is very memory safe. It tries to be very memory safe. The idea of Rust, okay, if I'm giving you a book to read, I don't own this book anymore. Read it and give it back to me unless you specify that, okay, like we both just read only this book and no one can touch it and write on it. So what if the same thing happens here? What if the Rust still owns the object and it gives C++ like an opportunity to read this object or like do something with this object, but the object goes away. So here's the functions we're gonna explore. So basically it's connect, we have client, the connect has a row pointer, just as an example for this thing. So row pointer is owned, the client is owned by Rust code. So basically when the C++ initialize the client and send the row pointer back, Rust owns this row pointer. C++ doesn't care about this chunk of memory, it doesn't care. Now, we do all of our stuff, again, we like try to connect to database and return the result back. Cool. What if the Rust runtime shuts down? It can happen because we can run concurrently different chunks of code, different pieces of code, and one can have like panic, everything crashes down, whatever, we shut down. What's gonna happen on C++ side? The C++ runtime is not bound to Rust runtime. It's still gonna work. And it's gonna go through the connect process. So basically, when you did deconnect, it started the connection future. So it continues to execute. It basically executes until the client object goes away. So basically, because Rust owns the client object, when the Rust runtime shuts down, it destroys all the objects it owns, including client. C++ doesn't know that. It just has a row pointer to a chunk of memory that is now free. So what do we get? We get segmentation fault. Not nice, but I told you before. So cool. How can we make that go away? How can we make it safe and avoid segmentation faults. Basically, the reason why it happens in the first place is because Rust thinks that it owns the object. Now, Rust needs to be aware of the fact that C++ owns the object too. So we could rob the client, or like row pointer, any row pointer, or like whatever object we try to share, within the reference counter. So basically, whenever we do want to send something to C++ side, we need to make sure that the reference count is increased, that the Rust is aware that the object is being held by something else, and we cannot just destroy it. So the way we can do that is basically keep a context of the client, so basically of the fact that the client is used within C++. We have reference counter on the Rust side. Then how do we bind it to the C++ runtime? We can send, again, with the call, like with the call do connect call to the C++ side, a clone, just a binary copy, a blob of data, a clone of a reference counter wrapped pointer, and send it back over the channel to the Rust side. That will ensure that the Rust side is aware of the fact that the reference counter is still non-zero, something is using it, and until it gets back this reference counter, it cannot really destroy the object. And this way, you avoid the segmentation fault. And here we are. Now it's the happily ever after, almost.
Any questions?
Thank you very much. I'd like to follow up the question on the lifetime. Let's say like you have the create an memory in C++ side. How do you let the Rust know that this thing is a copy and it borrows from C++? Because now you show that you increment the count, clone on the Rust side, but I want on the reverse side. Yeah.
Okay, so basically the question is, if we have an object within C++ and we send it to Rust, how do we ensure that the C++ is not going to destroy the object? Yeah. Okay, so one thing is it doesn't allow you, the bindings that don't allow you to have references to the objects. So where you can pass the objects within the boundary is only wrapped in it's either pointers or they're wrapped in this smart pointer context, right? If it's like a pointer, for example, and C++ decide to destroy it, oh well, this is an issue. So that's why you can use smart pointers within C++ side. But you can't use, I don't think you can use references to C++ opaque types within Rust. So the reason that the issue you're talking about can happen is because we use row pointer or any kind of pointer is going to be destroyed in C++ side. Yeah, it may happen. You have to, if you notice that, you have to make sure that this chunk of memory is wrapped in a smart pointer, and it's, yeah, or shared pointer or whatever. Or you have to be sure that the ownership is moved to the Rust side completely. Yeah. Well, basically you create, you create an object and you just send the pointer. Basically, C++ doesn't have a pointer addressed to this chunk of memory anymore. That's the only way. So, yeah.
Hey, great talk, thanks. On the last slide, on the lifetime thing, when you increment the ref count in Rust and pass it over to C++, and let's say the Rust side crashes,
yep.
C++ has no idea that it's a ref counted pointer, right? So will that lead to a leak? Because now Rust cannot clear that up. C++ has no idea that it has to clear it up. Will the client leak in this case?
So if for some reason Rust runtime decides to shut down and not destroy anything and basically leave a object with reference counter more than 0, I guess, not undestroyed, but it shuts down completely. Yes, it's in theory is going to be a memory leak because C++ doesn't know how to free this memory. But the thing is, on shutdown, Rust ensures to clean the memory. So you have to rely on this Rust cleaning up the memory. And so basically the idea when you send the clone to C++, Rust still has this object. So you have a basically container, and within this box there is a client object. And you send a clone of this box to C++ side, and Rust owns another copy. Rust owns the first copy, and C++ owns another copy, or clone. And when the shutdown is going to happen, Rust will know that this project is still in use until it receives the clone back and cleans it up. So basically the idea when you send the clone back to C++, when they send the clone in the first place to C++, C++ doesn't know how to destroy the memory. So it should send this clone back through the channel with the result of the future execution. And Rust receiving this clone will destroy it itself and like downgrade the reference counter. So yeah.
All right, sorry, one more question
Yeah.
on CXX in general. Are opaque types by default just modeled as pointers? Because Rust needs to have a size to really know about it, right? So how are opaque type modeled?
Yeah, that's correct. So basically, within the language boundary, the opaque types will be passed only as pointers, as or smart pointers or raw pointers. Yeah, Rust doesn't know about sizing.
Hello, hi. I have an observation and a question. The observation is awesome presentation. I really like the illustrations.
Thanks.
The question is, what tooling, if any, do you use, like sanitizers, address sanitizers, UBSAN, Valgrind, to have dynamic analysis that these things are going well, or do you just rely on compile time checks of CXX?
Yeah, so I myself used three things. Things. So first just the compilation time, basically it highlights the errors. Second, when we build stuff, we basically build with the memory sanitizers. So it will highlight the error if there is a memory leak. And the third thing that actually was super helpful is GDB. So basically a debugger, because sometimes if you work in a very async heavy environment, as we had in our project, the issues may happen on one of multiple threads, and you don't necessarily know what's going on, because these issues that I mentioned here, they are runtime issues, and that's the worst part, right? So when the program crashes, you basically connect to GDB trying to understand what happened on each thread, and basically it's very tedious, but you have to understand what code was being called, what happened, why this basically if it's segfault, why it happened, what kind of what pointer was destroyed. So yeah, so that's basically three tools that I kind of used.
One question, in general, the interrupt between the general interrupt of async, if the host language is Rust, and is the assumption right that on the C++ side there's always the runtime running on a separate thread?
Good question. I don't think that it's necessarily true that it's on separate thread, but I don't think I'm 100% sure. Sorry.
Okay, thanks.
Hi, great talk.
Thank you.
I have one clarification. With the reference, the counts, the increment there, I imagine if you're going to do a clone, yes, it increments the ref count, but it's still a Rust object that the runtime knows about.
Yeah.
I wondered, does it matter in that case, or do you need to call the explicit unsave, just increment the strong count?
Sorry, come again?
There is. I wonder how does it actually physically work when you clone to increment the ref count, that the Rust lifetime won't destroy it, because if you clone it, it's still kind of a Rust object, is kind of my point.
Okay, so if I understand correctly, so basically, so the client is just the pointer, right? Rust doesn't know the size of it, Rust doesn't know anything. Rust may not even know how to destroy this object, right? Or it can be like in Rust, it may be wrapped in the destructor and stuff like that. So, okay, now it knows how to destroy it. So when you do the clone, it's just a increment of the reference counter. So basically, at this point, Rust doesn't really do anything with this object. So so basically, you have to kind of be aware of, you cannot provide this reference counter, I guess, interface to the other functions within your code. But in the point when you actually call the asynchronous function, you have to wrap it up in the reference counter to ensure that in this particular like block of code, the Rust is aware that this object is currently shared between two different runtimes or like two different things. I don't know if I got your question correctly, but basically the idea is that we just increase the reference counter. It's still a Rust object. C++ doesn't know anything about this object apart from it holds the pointer to this object for a limited amount of time. So basically it receives the pointer and then it like sends the pointer or like sends the blob back through the channel. So C++, the only I guess action C++ needs to do is send it back over the channel, like basically call the callback that was, yeah.
Okay, thank you.
One more question?
Is there any way to automatically generate all the boilerplate for like just creating the channel and sending the value over the channel, or do you have to write that by hand for every single async call you want to do over FFI?
Yeah, so CXX doesn't generate that by default. You have to kind of like write it yourself. You can do, more of like, I guess, template work on Rust. So basically you can create like generic callbacks and then like use them throughout all the code. Just with like specific type that you want to send.
Yeah, so we have Lechazar here who will be speaking about saving $125 million. So if you ever have that amount of money, this is the greatest place to be. He's an active part of the Rust community, very interested in the aerospace community and started the Aero Rust community, and has been driving that forward and bringing the wonderful safety to that space, as well as just being a great person in the Rust community. So cool, give it up for Lechazar.
Thank you for the nice introduction. Hello, today we're going to take a look at the type system and how you can use it to your advantage. And yes, not burn your orbiter for $125 million. My name is Lechazar Lechev, as you already heard. I go by LPL at most places on social media. I love a challenge. Of course, I pick up my own challenges. I'm very excited about aerospace. Since 2020, I started working in aerospace. But rather than waiting to get the possibility, I decided to create my own. Since I was growing up, I was very excited about remote-controlled cars, planes, and boats, everything. Sadly, in Bulgaria, we didn't have the environment or the communities to facilitate my skills in that. So I took a different path for quite some time. And in 2020, I actually co-founded the Aero Rust community alongside one of the other two founders. And actually, the previous photo that you saw, this is in Cité de l'Espace. Sorry if I pronounce it wrongly, but this is in France, Toulouse, to be precise. And this is where, for the first time, I met in person the other co-founder, Jeremy. And it was really nice to share our passion towards aerospace and just enjoy the day around the museum. Now, Aero Rust, for those unaware, is the Rust community for aerospace applications. Our slogan or motto, however you want to call it, is that we are your launchpad to aerospace. And the community has three main goals that we're working on. The first one is that we want to create a space for anyone interested in aerospace and Rust to engage. No matter if you want to share your project or learn about a topic, you can always join our Discord server where most of the times the community resides and use this invite here. And of course, all of our open source projects are in the GitHub organization. The second goal of the Aero Rust community is to create learning materials and a knowledge base for anyone to get started with aerospace or learn about a specific topic. And the third and final goal is to, of course, work on the ecosystem and create all the crates necessary for aerospace applications. Apart from our main goals, of course, we participate in events, meetups, give talks and presentations like today. And as you can see on the left, this is our first iteration, our first version of the Nanosat workshop kit, which is an embedded beginners-friendly workshop. And our first iteration we actually did last year at the space conference in Plovdiv, which we organized for the first time. And the second day was the workshop day where we give out these kits for people to assemble, but later on also go through a few exercises to build a working application. So I'm basically this guy. Every time somebody wants to speak with me for space or spaceships, I'm the person you would like to speak with. Apart from my community work, I'm also a national point of contact for Bulgaria, which is a voluntary position of the Space Generation Advisory Council. And SGAC is a global organization which helps and facilitates young professionals and students interested in the space industry. This again is from last year, where we had our workshop. It's not very clear, probably, it's a small picture, but there are quite a few students that we managed to get into our workshop and the conference. This is our goal as SGAC, and SGAC was a partner at this event. You can also see Omar, another person from the Aerorust community, who was leading the workshop, and in this case he was explaining a bit about embedded before we actually started with the workshop. Now, I'm also a father, and this is my 6-month-old daughter. Yeah, I hid her face because you never know what will happen when she grows up, right? Maybe she'll be mad at me that I showed her face when she was a baby. But you can see that she's already interested in robotics, and I take every possibility to show her some interesting things and also talk to her as a rubber duck to try and solve an issue that I'm having. She might contribute sometime soon, but yeah, I just want to get her excited about science and technology, and I think I'm doing a pretty good job so far. Now, with that out of the way, let's talk about type-driven development, the main topic of this presentation. When we begin talking about type-driven development, of course, we have to start from the basics. That's why we're going to take a look at a few examples with primitive types and how you can utilize them to, of course, use the type system to your advantage. Then we're going to take a look at one example with new types, just for completeness. And we're then going to focus on the type state pattern. Last but not least, we're briefly going to take a look at cons generics, what's possible right now, what you can use them for, and a few examples. Okay. Primitive types. Most of you are probably aware already, but for example, if you have a value that can always be positive, instead of using a signed integer number, it's better to use unsigned integer number. That's already an advantage that you can take. And although the non-zero types are also new types in the standard library, I decided to include this example just to showcase what's included in the standard library. In the general idea and notion is that once you instantiate this non-zero structure, and of course handle the option underneath, in this case we are returning string slice error, you can be sure in your code that the value inside will never be 0. For new types, here I decided to create my own spacecraft name new type, which internally uses a string, but we don't make it public. And when we actually parse the value from a string value, we make sure that it always starts with an underscore. So when we use spacecraft name in our code, we can be sure that it always starts with an underscore. And of course, I have omitted here how you can implement display rather than using the internal string, so that you can hide the string value inside and operate with your own methods. Okay, so with that out of the way, the type state pattern. Before talking about the type state pattern, of course, it's good to mention the state machines with enums, which have some drawbacks, but we already have a use case with them using futures. And to take a look at futures, we're going to take a look at the enum poll in the standard library. So as you can see, we can have two states. One is pending and one is ready. Okay. However, with enums, we don't get this notion of which state comes before which and what are valid state changes. So if you have a simple future, even though it doesn't make really much sense in this case, if you have a ready state, you can always go back to a pending state. It's not enforced in the type system. And if you have, for example, an asynchronous function that has two await points, each of these await points has its own state machine with the poll enum, but also each await point is a state machine of its own. So once one of the futures is ready to continue, the data from that future gets resolved, right? And we can continue to the next state change, which is the next future. So the state machine flows correctly. Now you can still make futures which are type state. And this is the crate that you can use for that, the state machine future. It builds the type state pattern for you and makes sure that only valid states, you can move from one valid state to another, but never to an invalid state. And yeah, this is pretty much for futures. So now let's take a look at the other example. Yeah, actually we are going to take a look at a few patterns that I have observed in the community. And when talking about the type state pattern, we are basically using the power of generics and trade bounds. The first pattern that we're going to take a look at least I call it a mode of at least two. And if somebody knows a different name that I have, haven't seen, please come back to me when the presentation is over. I really want to see if there is a name for this pattern. Currently, it's the way you can circumvent the type system in Rust and provide both async and blocking API with the same structure. And this is useful in the embedded world, as we'll see in a bit with the examples. Since Rust doesn't have a syntax or doesn't have a way to define the same API as both async and blocking, this is the way to go for now. Wow, there are two more ways, but I'm going to mention them at the end of the presentation. Now, we're going to take a look at two examples. One of them is the unreleased version yet of the BMP388 sensor crate, which is a pressure and temperature sensor. And then we're going to take a look at the Embassy HAL crate for the RP2040, which has a neat feature that is not present in the BMP388, but it will give you the general idea of how to build such APIs. We're going to first start with the documentation. And I've created this crate just to give you the examples and to be more clear what's happening. So the driver crate has this BMP388 structure, and it can have two modes. One, the async one, and one for the blocking one. So these are unit type structs that you can use to define that you're either using the asynchronous API or the blocking. What does that mean with code? So you can see here that the mode actually requires us, we have a trait bound to this trait mode. And this is a public-facing trait. But when we take a look at the public trait, we also see that it requires us to implement this mode, which is a private trait. What this allows us to do, and it's not only used for this kind of scenarios, but it's common practice in the Rust community, is to define async and blocking as this public trait. However, because this trait, the other sealed mode, we can call it a sealed trait, is private for our crate, we are the only one, the crate developers, that can define what a mode is. Nobody outside of the crate can define what a mode is. So you can only have an async and blocking modes. What this allows us to do is, as a user of the crate, is to still abstract away the mode when we are using the API, but also use an async or blocking implementation. Now, as a summary, you have a sealed mode, which is a private trait that can only be implemented by you as a user or the developer of the crate. Then you have a data structure that requires a public-facing mode. And this public-facing mode has a trait bound to the sealed mode. The data structure itself can implement various traits for the various modes. And this is where we're going to take a look at the embassy crate. Just a bit of context, in the embedded world, just because we don't have this syntax to define both async and blocking APIs at the same place, the community has decided to create two different hardware abstraction layer traits, one for the blocking and one for the asynchronous versions. In this case, I will highlight just the important things, but you can see here that the SPI async version, I'm not sure if it's going to be visible, but it says that implements the embedded how async trait here. So this is the asynchronous with async functions. While this mode, which actually doesn't specify what's the mode. So here you can use either an async or blocking mode. They both implement the blocking trait for the SPI, which is really nifty, because if you think about it, and somewhere in the code you're using the async API, but one of your crates, the driver crates, is using blocking, you don't need to do anything else. You just use it, and that's it. Only for the async version, we have a special trait implementation. Now, this is one of the patterns. The other pattern is probably familiar to most of you. It's the builder pattern. However, we're going to specifically talk about the typed builder pattern, or the crate that allows you to generate typed builders. One of the applications that you can use this is for configuration. And again, we're going to give an example with the BMP crate. Some sensors don't always mention how in the datasheet, what is the default or what happens if you don't set up a certain register. In this case, we don't have that. Everything is defined in the datasheet. So we can use the default implementations. Let me see, config builder. Oh, yeah. So most of the fields have a default implementation, so something that by default is set up in the sensor when you want to initialize it. And what's interesting here to note, for example, the first implementation, and this is all generated by the type builder derive macro, is that you have all the fields here as generics, and actually here you can see that all fields begin as unit types. However, the crate generates all the implementations below, where, for example, the first one, you start with the config builder, and the first field, which is the address, is a unit type. Then when you call this method that to set up the address, you see that we only change the first field. By the way, is it visible from the back? Okay, perfect. And you can see, for example, for the second field, that the oversampling, again, we leave the rest of the fields as generics. But if we have the second field for oversampling a unit type, we can overwrite only this and leave the rest of the fields as they are. So whether they're set up or not, we don't really care because we are using generics in this case. What does that look like in code? Well, it's pretty simple. This is our configuration struct, and it's used to set up the sensor before we actually start measuring stuff, for example, the temperature. We have the address and also all these configuration values for filter, sampling rate. They all have default values, so that's why we just use field default. So it's not mandatory for the user of the API to use them or to set them up. They will be defaulted, but if they would like to do it, they can. Okay, next one. And this is one of my favorites. Units of measurement. So underneath, there are a few crates, but the one that I would like to share is the unit of measurement, or WOM crate, how at least I call it. Underneath, it uses the type num crate and implements the international system of units, but also the international system of quantities. And its application is, well, not to crash your space orbiter, or maybe mission critical systems. To be honest, everything that deals with conversion between different quantities and units is a good fit for this crate. The example that we're going to take a look at is the Mars Climate Orbiter, and how they managed to crash it because they wrongly converted one of the values. They were using pound seconds. They thought they were using pound seconds, so they converted it to Newton seconds, and they did a bad value of times 4.45. Here is a good time to mention that I didn't find conclusive information about this issue. There were quite a few articles that mentioned the problem, that it was communication problem between Lockheed Martin and NASA JPL. But this is the most complete version that I found of the everyday astronaut. Basically, the spacecraft was sending Newton seconds, while the ground software that Lockheed Martin apparently wrote took this value and thought it's a pound second value. And they converted it to Newton second, which meant that they wrongly convert one value to another. A caveat here, again, always check your sources. I found this article that was mentioning Newton seconds squared and pound seconds squared, which was wrong. And also this conversion calculator, which initially gave me wrong results. And I thought I found a bug in the crate, but actually it was the calculator itself. Now to take a look at the example, I have prepared. Okay, let's see. Maybe run the code first. So this example is actually for the space shuttle. I took, let me see, I think this would be better. Okay, here we go. So because we don't have public data for the spacecraft, the Mars orbiter, I took an example from Wikipedia for Newton second. And you have this example of the space shuttle launched from Earth to orbit, of course with some caveats like how much it weighs and so on. So I've taken these values here, and as you can see here, we have a speed of 8,050 meters per second and a mass of 132,000 kilograms and 500 kilograms. What we need to calculate is the impulse, which is in Newton seconds, and it's 1.07 times 10 to the power of 9. Good time to mention that Newton seconds is also equivalent to kilogram meters per second. Now, how does that look in code with units of measurement crate? First, we're going to take a look at the actual values here, and then we're going to take a look at how JPO actually got these values wrong from Lockheed Martin. We're just going to take the meters and define it as 8,050 and divide it by 1 second to get meters per second. So the speed over here is already meters per second. The types in the units of measurement, this allows us to, for example, add length and time. This would be a type error. It won't compile. So we know that length divided by time will give us meters per second in this case because of the two types here. Then we take the mass of the space shuttle, that was from Wikipedia, 132,500. And we calculate the momentum, which is basically mass times speed. Now, we can convert the units in units of measurement using the get function or method, and we just specify what kind of units we want them to get. In this case, it's kilograms meters per second. It's what we calculated, but we need to specify what we need to get these values in. And as you can see, we also have an assertion, and this is exactly the value of the momentum shown in Wikipedia. Of course, they rounded up the values, but this is the full value in Newton's seconds without scientific notation. Now, before we take a look at what they actually got, you can see that the actual newtons per second, as we saw, is this number, 1.07 times 10 to the power of 9. However, they showed this number, which has a difference of 4.45. So they were incorrectly guiding the spacecraft using these values. How does that look in code? What did they get wrong? So again, we have this number, which is 1.07, but this time we use pound force. And again, we multiply it by time to get pound force seconds. And we convert this to kilogram meters per second. And this is where we get the wrong value. As you can see here above, I've actually calculated the pound seconds correctly. And this, again, does the conversion from pound seconds to kilogram meters per second. But this time, we actually get the correct value, as you can see at the second row here. So if they used this crate, maybe they would have avoided burning the orbiter. Underneath the units of measurement, crate uses typenum, which is type level numbers evaluation. Its application is if you want to do a constant math operation. I'm going to give you a brief example of this, but you can go full crazy with it. I've seen a few examples. I haven't personally used it in a project, but it's a really cool way to use the types to do calculations. We have this compile time multiplication, and it has two generics, x and y. These are the values that we want to multiply together. The way this works is that you define a trade bound on x that you want to be able for x to be multiplied by y. And here it's how we combined each trade bound in order to do the calculations. The second trade bound, as you can see, we say that x as a thing that can multiply by y, and we take its output and say that it needs to be unsigned integer. In this case, if you try to say, for example, -1 for x times 5 for y, since -1 doesn't implement the unsigned, or actually the multiplication of the two numbers doesn't implement unsigned, the type system will just give you an error. It's that simple. And at the end, you can see that we use this output and just take the value out of it, because it's just a type. We don't pass anything to the actual function. And this means that the whole function is constant. How do you use this? Well, let me just show you that it works. I have another example, and you can see here that 3 times 4 is 12. The interesting part is how we call this function. As you can see, we are using a constant, which we call multiplier, and what we do is just call the compile time multiplication, but using these types provided from the type num crate. And both types, as you can see, are U3 and U4, which means unsigned integer. So the type system knows that these, for example, are unsigned, and that's why they can never be negative, and they implement an unsigned trait, and they can be multiplied together. And here you just show the constant value. Any questions so far? So, yeah, to repeat the question, when can we use this? Well, basically wherever you want to do computation with the type system, to be sure that somebody cannot multiply a negative number times a positive number or something like that. So it's just a way to use the type system in your advantage. It's tricky to use for everything. It doesn't make sense, right? But if you really want to be sure on a compile time that, let's say, some calculation is correct, this is where you can use it. I've seen people using it for embedded, but it gets very long when you have some formula that you want to express in types. It gets the trait bounds get very, very long. But it is possible. Yeah, that's what you do, yeah. Now for cons generics, and again, if you're into the embedded ecosystem, you're already aware of heapless. It's a crate that provides you structures like string and vector from the standard library, but with fixed size. So the API is a little bit different because, of course, you can run out of memory inside. If you have a vector of 5 elements and you want to push a 6th element, you need to handle this overflow. And it's generally used whenever you want to store stuff, but you don't have access to an allocator, which is for embedded systems. Another example that you can take a look at for cons generics in the wild, it's the frame buffer from the embedded graphics. What they do there, they actually use a few cons generics, but for the frame buffer, they have width and height, so they can calculate a frame buffer, which is exactly your width and height of the picture you want to draw, for example. And they use a few other cons generics. And you can also take a look at the builder pattern, which again has const typed builder instead of just typed builder, which is pretty much the same thing that we saw with the type builder, but with cons generics, just a crate for that. And units of measurement, I actually contacted this the maintainer or the creator of this const units crate. It's still work in progress, and currently it doesn't build. Sadly, I cannot show it to you. But it uses a lot of nightly features, sadly. So it will take some time to get this into stable. And as you can see here, we have const ops and const utils that the maintainer created, because we don't have const operations in the standard library yet. And yeah, so I wanted to show this, but I had to fix the build first, then show it to you. So it was a challenge. As examples, how you can use const generics, I have a few examples that maybe make sense in some cases, maybe they don't. But let's take a look at them. In this case, we imagine that we have a battery management system, and we have a voltage divider. A voltage divider basically uses two resistors so that you can divide the voltage that you want to measure with your microcontroller, because, for example, your battery can go up to 4.2 volts, but your microcontroller can only, your pin on the microcontroller can only go to 3.3 volts. So a voltage divider is something that you can use in order to get half of the value, for example, and then you just multiply it by 2 to get the actual voltage. Again, it really depends what's your use case, because in this case, the two resistors, they always have minor differences. The best resistors are plus minus 1%. So if you want to scale this to multiple devices, maybe it doesn't make sense to have const generics with this. However, you can plug directly your own resistor value here and get a const generic voltage divider that can be used in your code. So bake your values inside the type system itself. Of course, if you're doing multiple devices, that doesn't make sense, because for every device, you need to change this, flash the device, then take another device, measure the resistors, and do the same, which is not very scalable. In the wild, you also have the GPIO pin of ESP HAL. As you can see here, they use a const generic U8 to specify the number of the GPIO that this structure is focused on. And it also has a mode generic, which is again the mode of 2, I would say, pattern. And you can see here that you have a GPIO pin input, for example, mode, but you have also, let's say, output, I think, inverted input, and probably, yes, here, output. So this is, again, your mode. And as an example, I also created this small struct, again, inspired by that, where you have the pin number as a const generic, and you have the voltage mode for your pin, so 3.3 volt or 5 volt, for example. The rest of the examples, yeah, probably next time. I've also prepared some of the resources for this talk, and in general, things that you can check out. On the left, you'll find type state pattern. You'll find, for example, most of the information that I shared here, but condensed from Let's Get Rusty. Also the state machine pattern, or understanding futures. On the right, I've shared 2 more crates that can be used for units of measurement, and also the discussion of inside the units of measurement crate for const generics. Remember how I said earlier that there are 2 ways or a few ways that you can create both asynchronous and blocking API? Well, these last 2 crates are exactly that. It's macros that can help you strip out asynchronous code and basically have one API for both synchronous or blocking API and asynchronous. And for example, I've seen people using futures to either allow one or the other APIs. Now I still have time, so there's a surprise. And you see this t-shirt? That's actually one out of two, the first t-shirts of the Aero Rust community. And I have a second one, which is not white, by the way. It's black. And I want to give it away to somebody. So it's M size, so if you think that it won't fit you, probably don't raise your hand. But can I have hands for anyone that wants the t-shirt, and I'll just pick one to have it or throw it? Ah, that's actually a good idea. Okay, ready? Okay, ready? Nice. So you now have the limited edition of 2 t-shirts, the first 2 t-shirts of the community. Of course, you can find the slides because I've included quite a few resources and links inside the slides. And yeah, do you have any questions?
Thanks for the talk. Going all the way back to the async type state stuff at the beginning, I'm not sure I followed what the advantage was of making the async a type parameter rather than just having 2 different functions, one async and one not.
In a nutshell, you will still have both. In the example of, let's take a look at Embassy, because I think it's very clear here. You see the methods on the side. You have blocking read, blocking transfer, which is the default. That's why you can use both blocking in async or blocking mode. However, because the embedded world is divided into basically the blocking traits and the asynchronous traits, in this case you still have one struct, but it handles both traits. So this is the advantage. Instead of, for example, going and copying all the code and just adding await, you can condense this into a single structure to house all of this, rather than duplicating your code. Because I've seen that as well. I've also experienced it and worked with that kind of code.
You mean because the structure definition itself needs to be different for both cases?
To some extent. They implement different traits. And the mode is what says which trait you're implementing, basically.
Okay, thanks.
Any other questions?
Any other questions? Okay, cool. Thank you for the talk. That was really good. Okay, sweet. It's lunch now, I think, so that'll be in the main hall. Okay, cheers, guys. concoction of languages in there. This is bound to be a very interesting talk. So cool. Nicholas, all you.
Yeah, we... Cool, thanks. Yeah, we kind of hit the Hacker News triple-double there. So, yeah. Are my slides working? Yeah, they were. Is my... Okay, do I just need a... Oh, there we go. Yep. Triangle. Cool. So, I'm going to make a bold assumption here and say that we all wish we were writing more Rust, right? Like, we all want to write more Rust in our day-to-day lives and, have our companies move to Rust and so on. And a common way that we do that is to rewrite it in Rust. This has become a meme, a mission, in some cases almost like a threat. Like, we're going to rewrite everything in Rust. But today, I'm not here to talk to you about rewriting, because rewrites are hard, and they're kind of scary in a lot of ways. Like, when you rewrite, you're devoting yourself to often a multi-month, possibly multi-year plan, where you have to learn this new technology, and you have to then build out this system. You're losing users, you're breaking changes, and you're introducing new bugs. And it can really cause a lot of pain and suffering and hurt your company. So I'm not going to talk about rewriting. Instead, I'm going to talk about porting. Now, what's the difference? Well, it's a slight bit of semantics, but a port to me is something that is incremental and does not start from the ground up. When you port, you're moving individual pieces to Rust, and oftentimes you have to live in this combined ecosystem for a bit, where you have a little bit of Go and a little bit of Rust. So, hi, I'm Nicholas. I work at Vercel on Turborepo, and I'm here to talk to you about porting Turborepo to Rust. So what is Turborepo? Turborepo is a build system for JavaScript. It allows you to scale up your JavaScript builds, often inside a monorepo. And here's an example of that. So let's say you have a shared UI library that's used in both a web app and an internal docs app. Normally, when you build this, you build it kind of sequentially. If you use something like Yarn workspaces, you first run the lint tasks, then the build tasks, and then the test tasks. And it's not really that ideal. With Turborepo, you can do it in parallel. And even better than that, you can cache the output. So if you run this again, say if you run it on your local machine after running it on CI or vice versa, Turborepo will read from a shared remote cache. As for the architecture, it's a native binary compiled for 6 targets. That's x86 and ARM times Linux, Mac, Windows. By the way, I love the cursed Linux, like the reverse image. And it's about 70K lines of Go. And that consists of the main execution pipeline. There's a daemon for performance improvements. There's prune, which allows you to strip out a monorepo into a single package and its dependencies. And then there's the auxiliary commands like log in, log out, and so on. So let's go over the execution pipeline. Basically, it loads in your config from the file system, environment variables, flags, and so on. It then builds up what's called the package graph, which is the dependency graph of the different packages within your monorepo. So again, if you have a UI library that's used by a web app. And from there, it spins up the task graph, which is a graph basically of the different tasks that need to be run. So you can have a build task that depends on a lint task. You can have a build task that depends on the build task of a package's dependencies, and so on. From there, we traverse this task graph and execute. If we can determine that a task has already been run, we cache it and don't run it. And at the end, we build up a summary of the run, which can be uploaded to Vercel or shared however you like. So why did we decide to port? And take some more. Ooh, screen of death. Fun. Yeah, the cursed water. Let's see. Is it? Oh, there we go. Nice. So the first reason why we decided to port was really around alignment. Now, Go is a really great language in a lot of ways, and specifically, it's really great at writing a web server run on a Unix-based system. And a lot of its abstractions are based around that assumption. So the classic one is file permission codes. Go will let you set a Unix-style file permission code. And that works great if you're running on Linux, but it doesn't really work great if you're running on Windows. In fact, if you do it, Go will basically just lie to you and say, yeah, you set that file permission code, even though it's not really doing that because Windows doesn't have a concept of file permission codes. Whereas with Rust makes sure to get every detail right here. If you want to use file permission codes, you have to annotate the code as Unix only. If you want to use Windows API for file permissions, you have to annotate the code as Windows only. Next up is ecosystem. So Rust has a lot of really great libraries, as I'm sure all of you know, and they're really helpful because TurboRepo is fundamentally a product that has a lot of interaction. We have to parse a bunch of different formats, we have to interoperate, we have to do a bunch of different things, and having a good set of crates makes this a lot easier. We also have a sibling team, TurboPack, which is our Rust-based successor to Webpack, and we wanted to share the same code. So if we write like one file watching crate, we can use it between TurboPack and TurboRepo. And finally, Rust has become the sort of lingua franca of JavaScript dev tools. Like, it's used in a lot of different projects like Biome, SWC, and API, and we want to use these projects in TurboRepo. And later you'll see how we've, in fact, started using them post-port. So how did we start to port? Now, you can imagine you could start from the ground up. You start with a command line, and you build a rudimentary package graph, and you build a task graph on top of that. But that doesn't really work, because you got a lot of stuff to build, you know? Again, this is about 70,000 lines. It's a mature product. There's a lot of features, and building all of them in a reasonable amount of time isn't feasible. So we decided instead to not do a ground-up rewrite, and then start by incrementally adding things. So the first thing we built was actually a new feature. And that feature is what we call the Rust shim. So the architecture is as such. It's essentially a Rust wrapper around the Go code. We compiled the Go code as a C library, and then we linked it into a Rust binary. And what we used this for was to build what we call global turbo. Global turbo allows you to run TurboRepo as a global binary, like cargo, but when you run it inside a repo, it will detect that it's run inside a repo and find the local version of Turbo and essentially delegate to that version. And this is really nice because it allows you to pin your version of Turbo, but also use it as a normal command line utility. And so what's nice about this is the Rust code really didn't have to do much. All it had to do was essentially infer a repository and then just call the Go code. That's it. After that, we decided to port the command line parser. And this was a natural next step because we already had to do a little bit of command line parsing for the shim. So we just decided to port the whole thing. And we used a nice library called Clap, which allows you to generate a CLI parser pretty easily. And then from there, we serialized that to JSON and sent it to the Go binary. The reason we use JSON here is because we didn't really want to write a bunch of types in C, because again, that's the interop layer, is C. And no one really wants to write cross-platform C types. So instead, we use JSON to move it. Now for some shipping issues, because nothing goes according to plan. So the first one was, of course, Windows. Now, Windows has two versions of the C standard library. It has MSVC and MinGW. And on Windows ARM, Rust actually doesn't have a MinGW Windows ARM target. So we couldn't actually build this for Windows ARM because Go only supports MinGW. And so we had to basically just build for x86 and rely on Windows ARM's built-in virtualization. And like, while that would have some performance impact, we figured that for the duration of the port, it would be acceptable. Next up is Alpine. Show of hands, who here has used Alpine? Nice. Well, I'm kind of sorry, but anyways, Alpine, if you're not familiar, is a distro of Linux that's particularly lightweight. And what makes it lightweight, in part, is that it does not have a version of glibc, which is the most common C standard library implementation for Linux. And normally this isn't a big deal because there are compatibility layers that smooth this over. You just install a library and you can use glibc. But we wanted to support particularly old versions of Alpine. And when you're supporting an old version of Alpine, the compatibility layer works with an old version of glibc. And that doesn't really work when you're compiling in a relatively new toolchain that demands a new version of glibc. And so we decided instead to use Muscle, which is an alternate version of the C standard library that can be statically linked. Static linking basically means you include it in the binary, so you don't have to worry about the OS providing it. When we did this, well, we segfaulted almost immediately. And there wasn't really an indication of why. In fact, when we looked with a debugger, we figured out that the segfault was coming from the Go runtime and that the stack was corrupted, and basically nothing made sense. So after a lot of Googling and banging your head against the wall and trying to figure out what's going on, we figured out that from a 9-year-old GitHub issue, isn't it always fun when you find those like 9-year-old GitHub issues that have like 200 comments? Lovely. But yeah, and this issue basically indicates that you cannot build a Go binary as a shared library with Muscle. If you do that, just things don't work. So we had to come up with a different approach. The new approach is 2 binaries. We build a Rust binary that then calls the Go binary. And we pass the args, again, as JSON, but this time just as one big command line argument. And this worked pretty well, because we were already doing a serialization, so it was really just a matter of like passing it through a slightly different manner. So with that, we were able to ship TurboRepo 1.7 with the Rust shim. Next up is the Go sandwich. So at this point, we had to make a decision about how to keep porting. We ported a lot of the low-hanging fruit, like log in, log out, but we still had the main execution pipeline. And this was kind of tricky, because basically the first thing you do in an execution pipeline is spin up the package dependency graph. And graphs are not really that fun to send over JSON. They're not very serializable. And so we had to figure out how to keep porting. Another aspect of this is that the package graph is really the core abstraction of TurboRepo. If you mess up in any way, everything will break. And so we wanted to make sure that we had a good infrastructure set up before we ported the package graph. One idea we had was this kind of funky idea of using the Go binary as kind of like a trampoline, where you like repeatedly call it, and then it like brings you to different parts of the pipeline and passes data back and forth. That didn't really work too well. Another idea was to use the daemon as a way to port by essentially porting the daemon first and then using the protobuf info there to port incrementally. But the daemon was meant as an optional improvement, and so moving it into a critical part of the pipeline meant that we'd have to fundamentally rethink how it was implemented. What we ended up coming up with was what we call the Rust Go Rust sandwich, or the Go sandwich for short. And yes, it is as absurd as you think it is. It essentially allows us to port individual dependencies from Go to Rust. And what's nice about this is we can kind of start porting at the leaf nodes and port various contained chunks. So you can port our Git integration or port our lock file analysis without having to touch the core of TurboRepo. Another nice part about this is it provided a very regimented way of porting. The way we'd start is we'd split out the Go and the Rust implementation into 2 separate files, which we would gate using a Go build tag. From there, we'd build out the Rust implementation, and of course, write a bunch of tests. And actually, these tests would often be written in Go, because then you could cross-test, you could call the Rust version and compare with the Go code. And then from there, we would be able to ship it. But of course, more shipping issues, because when you build your Rust Go Rust monstrosity, nothing goes to plan. So again, let's remind that we're building for 6 targets. And when you build for 6 targets, you end up having to do a cross-compilation. Basically, you're compiling on a specific architecture for a bunch of different architectures. Maybe you're building on a Linux x86 machine for Windows ARM. And when you're doing cross-compilation, you end up in this tricky situation. Specifically, the Rust code uses a bunch of C libraries underneath the hood. That may be libgit2, that may be libunwind, which is actually used in the Rust runtime. And because Go is the end consumer of these, Rust can't actually link them for you, because Rust is just building a shared library. It can't do any of the nice, fun cross-compilation for C that we expect it to do. And so you end up having to cross-compile your C libraries yourself, which is not fun and pretty painful generally, except if you use Zig. Yep. We ended up using Zig because Zig has this wonderful C compiler called ZigCC, which allows you to do easy cross-compilation. Specifically, it allows you to easily include various libraries because it bundles all the different sysroots necessary for the different targets. And so with that, we're able to get the sandwich out the door in Turbo 1.8.6. So finally, we have the run outline. So at this point, we started to hit the limits of the sandwich. Specifically, we reached a point at which we started to use more async code. One example of this is our HTTP cache, where we have to fetch cache entries from a remote server. And we didn't really want to tackle the issue of interoperating Go's async code with Rust's async code. I mean, we could have, but it was frankly a little terrifying. So at this point, we decided to start building a full run outline. And this was essentially an all-Rust execution pipeline with the unimplemented parts stubbed out. So we'd have like a stubbed out package graph, stubbed out task graph, and so on. And we'd start to slowly implement them. And we added a flag to switch on to this code path. Now, at this point, you may be thinking, isn't that a rewrite? You know, you said that we're not doing rewrites here, and but isn't this? And yeah, it kind of is. But it's important to remember that the shim and the sandwich both bought us a lot of time. Like, we managed to port a significant chunk of the code base without stopping the world and doing a rewrite. In fact, we're able to ship quite a few features while porting. But at this point, we did have to kind of say, look, we're going to do a rewrite. And this did lead to a question of unused code. As a whole, unused code, I think, is one of the most dangerous things you can have, because it's code that fundamentally is not being exercised and not being tested in a real way. I mean, sure, you can write tests for it, but tests only test those specific scenarios. They're not a replacement for people actually using it. And so we had to figure out a way to execute the code that we were building. We didn't want to build this whole pipeline and then release it to the world and then have like 1 million bug reports flood it. The first way we did that was with prune. Prune, again, is a command that allows you to strip your monorepo down to a single package and its dependencies. So in this case, if you prune A, you get A and all of its dependencies. And this is really nice if you're running a Docker container and you don't want to include your whole monorepo in there. So prune uses the package graph, and so we were able to test the package graph and also our lock file analysis using prune. Next up is hashing. So hashing is at the core of TurboRepo. We use hashing to basically take all of our tasks and all of the task inputs, so in this case, this could be files, environment variables, packages, and so on, and we hash that into a single hash, which we then use to index into the cache. By the way, task, hash, and cache all sound alike, and that was really annoying during this port. And so we decided that we wanted to keep hashing stable between Rust and Go. And the reason for this was it allowed us to have a very specific testing point. If we knew that both hashes were the same, we could be reasonably sure that the implementations were pretty much identical. The issue with this is the Go code used a Go-specific hashing algorithm. Specifically, it basically took all the inputs to the hash and printed it using Go's sprintf implementation. We didn't really want to implement Go's sprintf in Rust. That seemed like a waste of time. So we had to figure out a way to move the Go code to the same hashing algorithm. And for that, we used Cap'n Proto. So Cap'n Proto, if you're not familiar, is this wonderful serialization format that's defined essentially byte for byte. And what's nice about this is we knew that the Rust version and the Go version were going to produce the same output. And in fact, it also included some canonicalization code so that you can definitely ensure that it's the same output. And so with that, we were able to move the hashing to the same algorithm and confirm that the hash is matched in both Rust and Go. And in fact, we ran this on all of our tests. So with that, we had a pretty straightforward process for releasing. We basically moved them both to Cap'n Proto, then we burned down the broken tests, we ran the run outline on all of our existing tests, and then from there, we dogfooded the Rust version internally at Vercel. We moved our big monorepos for our front end onto it, we moved some other pieces onto it, and once we reached 72 hours of no bugs, we shipped the all Rust version with a Go fallback flag in case bugs happened. And with that, we were able to ship Turbo 1.11 with all Rust. Yes, thank you. Thank you. So, what did we learn here? Well, first, I would say that there was a lot of success. We managed to move 70,000 lines in about 15 months. And this may seem like a long time, but all things considered, I think it was a pretty good success because we were able to do it while still shipping code. Like, there's a very big difference between 15 months where you're radio silent and your users aren't getting anything from it, and 15 months where you're still shipping features. And we didn't get bogged down in second system effect. So if you're not familiar, second system effect is this idea coined by Fred Brooks in the Mythical Man Month. And it refers to the idea that architects tend to have a lot of trouble with their second system. They try to implement all the things that they didn't get to in the first system. They try to make it perfect. They try to fundamentally rethink things. We didn't do that. We kept it very simple. And finally, serialization was a big win. We leveraged it in basically every part of the port. I forgot to mention that in the sandwich, we used protobuf to communicate between Rust and Go. And that was a big win, too, because we didn't, again, have to think about C types at all. What are the things that we could have done better? Well, first is really about maintenance. And tied into that is our porting philosophy. We arrived at this idea of like a strict port somewhat in the first third of the porting process, I would say. Before that, we had this vague idea that we could improve things while porting. Maybe we could remove a deprecated feature or add testing. And we quickly realized that that wasn't really feasible. I mean, we could do some, but we couldn't change things in the middle of the port. We had to keep it strict. Another aspect of this is our testing story. Overall, it was pretty good coming in. We had comprehensive tests on multiple levels. But of course, we could have had more. You see, when you're porting, you have to think very, very carefully about semantics. when you're writing the first implementation, it kind of doesn't matter in specific cases. Like the semantics are the semantics. If you load config with your environment variables first and your flags second, I mean, sure, that's just how it works. But when you're porting, you have to think about that very carefully, because if the config library that you're using in Rust loads it in a different way, well, you suddenly introduced a breaking change. Next up was really build process. Builds were slow, really slow. This is particularly ironic considering Turbo Repo is a tool for speeding up builds. But you know, when you're building a Rust Go Rust sandwich, it just takes forever. And finally, we should have shipped nothing quickly. And what this means is that with each strategy, it would have benefited us to ship the basic minimum version of it at each point. We chose a strategy, implemented a bunch of code, and then shipped it, and this created a lot of risk where if the shipping process hadn't worked out, we would have been stuck with this code that we couldn't ship to users. So now, post-port, we're doing some really cool stuff. One thing that we're doing is we're revamping our errors. So for this, we're using Biome to parse the JSON. And then from there, we're using Miette, this really nice error printing library, to print the errors. And this is way better than our previous errors, and something that we just couldn't have done in Go. Miette doesn't exist in Go, there's no equivalent, and there isn't, as far as I know, an equivalent JSON parser that also gives you the span info for the parsed JSON. And then another thing that we just shipped in 1.13 is an experimental mode for a new UI. And this is built using a wonderful crate called Ratatouille, which allows us to show a more visual indication of which tasks are running and how long they're taking. So with that, that's it.
Any questions?
Hello? Yeah. Do you see from your users, do they notice that after the rewrite that app is, I don't know, better, less flaky, stable, I don't know, like more featureful, feature faster? Like, do the users notice?
So this is actually a really good point. We have been kind of puzzled lately because our GitHub issues are really down. Like, we thought at first it was just, you know, a sort of post-holiday quietness, but no, our issues have been consistently down and very, very, so it seems like, yeah, we are a lot more stable and people don't seem to be having issues. I mean, if you use Turbo and you have an issue, feel free to talk to me, but as far as we can tell, it has actually had a material improvement in stability.
Hi, great talk, thank you. I'm wondering if you can talk, you talked at the beginning about some of the issues that motivated this incremental port to Rust, but I'm wondering if you could talk about like how that decision got made, like maybe you were aware for a long time of some of these issues that Go was creating, and then, I don't know, someone just finally brought up Rust as a potential solution, or?
So funnily enough, I actually didn't know the backstory because I came to Vercel partially for this port, but I talked to some of my coworkers and it did seem like there was a general sense that like we were moving to a more Rust-based world for JavaScript tooling between, you know, our Rust compiler and Next.js, SWC, TurboPack, and I think also, yeah, there was just a sense of like this would unlock a lot of different features and different things that we could do.
Yeah, hi, great talk. How many people have participated in this initiative? And would you say that all of them were doing both? Or some of them were just like exclusively working on features in Go and some of them were like working like 2080?
Very good question. So there were about, I want to say 7, 8 people on a team, but only like maybe 2 to 3 at a time focused on the port. A lot of them, the others were working on Go features. Also, we had like a total baby boom in the middle of this port, and like everyone went on parental leave. So actually, like, I didn't want to bring this up, but yeah, like, all things considered, this port went really well, considering we had like half the team on leave at one point.
Yeah, and I have a follow-up question. So like, when people came from parental leave, or when people started interacting with the proceedings that you had in porting parts to Rust, how smooth of the experience was it for them? Was it like, I don't know, DevOps adoption shock, where like, wow, my code has to be deployed, I never thought about it? Or was it like organic, like, I don't know, something else?
Yeah, so I would say that maybe half of our team, or a little less, maybe like a third, had prior experience with Rust. And so they had a pretty smooth time, of course. The other 2/3 of the team seemed to learn pretty quickly. I mean, frankly, I was very impressed with my coworkers and their pull requests. I remember reviewing one where I was like, wow, this might be better Rust code than mine. So yeah, I think overall it was very, very smooth. Surprisingly so, in fact.
Hello. One question regarding the hashing that you mentioned. I've understood that you essentially use the hash function, how it is implemented in Rust, and you fed the data kind of from Go over, and you use Captain Proto for that? Or can you elaborate?
Yeah, so this wasn't, not quite. So we implemented both in their own separate pipeline, but then actually what we did was in the Go, so with the main like Go pipeline, in our debug mode, we would actually run the entire Rust pipeline until we got to the hashing point, and then pass those hashes to the Go code, and then when the Go code computed the hashes, we would compare the two. And of course, that would only run on debug mode. We never ran this in prod, but yeah, that was like pretty straightforward in like getting you, like making sure that all the hashes were the same.
All right, thank you.
I guess in terms of build times, like you said your build times went up. Are you at the point where they're coming down again, or?
Yeah, definitely. They're way better now. I think we still have to invest a little bit of work because we have a bit of a monolith crate, and that is creating some slower build times, but overall it's way better.
As in like 3x better, or?
Yeah, like significantly better. It also helps that we're using SC cache, and SC cache works a lot better when you're building Rust. In fact, there was one small trick that we used for the build times where we specifically had the Go build part be a different crate, and then we had a turborepo lib crate that contained the majority of the Rust code, and so you could build that without having to also build the Go code.
I was wondering, when you were rewriting all the features into Rust, would you ever add new features during the rewrite, or were you always aiming to have the exact like feature parity?
So when we came in, we thought that we could do it, but it turned out that no. Like we had to keep things very, very strict. And you know, this that sometimes is really frustrating. Like it killed me to have to port things that were literally deprecated features, but we knew that like we couldn't have the issue of, because we always wanted to be able to revert back to the Go code. So at each step, like you could just say like, I want to run the Go code only. And we didn't want the feature to kind of disappear depending on which version of the code you were which version of the code you were running.
Hi, thank you for a great story. I wanted to ask, before you decided to split the thing into two binaries, how did it technically work? Like, were you meeting object files from the Rust compiler and then statically linking it with CGO, or somehow differently?
So for the shim part, we were emitting, Go has like a build version called C archive, and so we were using that. And then, yeah, we were essentially just linking that into the Rust code. And it was, yeah.
Oh, so it was the other way around. So
yeah, in the beginning. And then when we reached the sandwich, we did the opposite. We linked the Rust into the Go code.
Okay, then the follow-up question. Like, obviously from the Rust, like for the interop, you had to do like RepoC and external, all the things. So you were pretty limited with the data types that you were able to expose. Like, how were you dealing with that? Were you using some sort of serializer to like a byte stream or?
Yeah, so in the shim, we serialize the JSON. And then with the sandwich, we use protobuf, because protobuf meant that we could generate both the clients. And we already were using protobuf for our daemon, so it didn't add anything.
Okay. And for the last question, have you considered the option of like dynamic linking before you split it into binaries?
I don't know if we ever considered that. I think it was just too, I don't know. I think we just weren't comfortable with that, especially with cross-platform. It seemed a little bit.
Okay, you just thought that at this point you should definitely split it into two binaries and it would be easier. Okay, got it.
Yeah, I mean, I think at that point, like, we just wanted to do something that was very simple, and we knew that like binary execution was something that we could rely on.
Thank you very much.
How did you decide what to port over first, or was there even a priority?
I think we decided basically because it was like Global Turbo was something that had been asked for a really long time. So we wanted to provide something that people were excited about. And we also knew that it was something that didn't require much information or much integration with the Go code. Like, all it required was essentially a wrapper around the front door. And from there, I think we just started porting the easiest things first. And then from there, we there were also some false starts, of course. At points we tried to port things and then realized, okay, we need to back up and think about this a little bit more. I think like the outside-in approach worked pretty well for us, because porting the core abstraction, I think a lot of times we like to think that that's like the most interesting thing, and therefore the thing you should port first. Like, I think a lot of us tend to think of like web apps as like the database tables, and then you add everything else. But that's a kind of dangerous approach, because the fundamental data structure is the thing that will cause the most bugs if you mess it up.
Great talk. You mentioned you use Zig as well at one point, obviously for good reasons, to improve the kind of build. The question I would have, or a question I do have, is essentially how much Zig do you use currently in Turbo Repo, and what was that conversation like when you had to add another language to Turbo Repo when you're already porting from Rust, so Go to Rust?
Yeah, well, I proposed that we do a Zig rewrite next, but that's not popular. But no, in all seriousness, we didn't really use any Zig code. It was mostly just for the tool chain. And I think, like, to be frank, this was kind of a long shot. Like, we were trying other approaches, and it wasn't really working very well. And I'd heard that Zig CC was useful. I had played around with it for compiling to WebAssembly. And so we just ended up using it as a compiler, essentially. No Zig code in there.
That was my question, but thanks. I mean, I actually wanted to ask you a little bit more about Zig and like what it is, because I don't know if everyone knows about Zig here. I certainly don't. For me, like, it's something that my ICFPC team brings up every year. Like, okay, let's not do Rust this year, let's do Zig, and then everyone's like, no, and So what's up with that? And
yeah, I mean, Zig is this very cool systems programming language that is, I would say, if Rust is like a C++ successor, Zig is closer to a C successor, and it's meant to be very low level, very efficient, and it comes with a lot of compile time features, so you can essentially implement things like generics using compile time code. I think it's very cool. I haven't used it much personally, but I do think that, if it fills a niche that is necessary.
Hi, I'm back. Sorry. um, because you brought up at one stage you had this sort of mixed Rust Go setup where Rust was doing the final link, and in another case you had Go doing the final link. So sort of a two-parter. One, would you ever consider having a long-term situation where both Rust and Go are in the mix rather than just having that be in a transitional stage? And two, if you did have to, would you prefer to Rust do the linking or Go do the linking?
Sort of,
Thanks.
yeah. For the first part, no, I would not want to do that. Everything was so much harder in a combined world. The tooling was harder, it was not fun. And there were so many conversations we had where it was like, okay, we're gonna do this post-port, we're gonna do this post-port. And which would I prefer to be linked first? I would say, so my personal preference would be that Rust be the final linker because Rust has a better facilities for this as a whole. I will admit I'm biased because I fundamentally know Rust better than Go. But I will say that pragmatically, Go linking finally makes more sense because Go has this runtime which doesn't seem to play well as a shared library. Whereas Rust, you can kind of imagine it as this just black box where you feed in data, you get out data. Go kind of expects the whole world. I mean, we don't have to keep, yeah.
This wasn't particularly about the port, more about performance. And you had your text UI for working at what's building currently.
Yeah.
Is that based on Tokyo tracing, and could it be pushed into an open telemetry style reporting system, or is this just a UI kind of?
This you're talking about?
That thing. Yeah.
I don't think we're doing anything with open telemetry, but if you want to open an issue, we'll definitely consider it. I think we're always open to new ways of integrating and visualizing execution. This is just a UI built with Ratatouille. It's not anything with open telemetry as far as I can tell.
Okay. Yeah, no, we've just got in our company, we've got a really horrific set of yarn scripts. And I was like, fuck it. And I just built a thing that pretended to be yarn and pretended to be bash and just reported everything that got sent to it to open telemetry, and suddenly we can actually understand what we're doing.
Oh, wow. Very cool.
But yeah.
Please give a final hand for Nicholas.
Thank you.
everybody. Cool, so for this talk we have Nikita. He works at Prisma and has been writing Rust for about 1.5 years. So he's replacing Ellie, who is not here because she has COVID, and was given about 48 hours to prepare this talk. So you will 100% enjoy it, and probably give him an extra round of applause at the end. But cool, yeah, floor's yours.
Right, test. Yeah, I can hear myself. Hello, everyone. Let's talk some actors. First, a round of introductions. My name is Nikita. I have worked on a bunch of databases like MongoDB and ClickHouse. Currently, I work on Prisma. My main focuses are system programming and everything related to data. Before we dive into the actor land, let's discuss what they are. I'm sure a lot of you have already heard about the actor model and maybe know something about it, but just to quickly recap. Actors is a way of thinking about concurrency. It's a model for concurrent programming, which in layman terms can be presented as a bunch of single-threaded tasks executing concurrently. One of the features which usually stands out in actors is the fact that there are no locks, no atomics or conditional variables involved, because there is no shared state. Your actors cannot access to the same memory location ever. Instead, actors use message passing as the main synchronization primitive, so the only way to actually talk to our actor is by sending a message. When I first encountered this model, it felt weird, to be honest. I was taught in the university to think in terms of locks and atomics, and now you're saying that, hey, I will be memcpying data all the time, but it actually has some interesting properties. The fact that each task is single-threaded makes it easily parallelizable. Consider an example of an HTTP server. If each actor is handling a if an actor handles an HTTP request and maybe your system is under load, you can just spawn more actors, and each of them will have, you will have the increased capacity of your system just by spawning more tasks without any code change involved. Since there is no shared state, there is no data races. I say that in quotes because there are many creative ways to create a data race with any synchronization primitives, but it is significantly harder with message passing because of some ownership. Because when you are passing a message, you are relinquishing the ownership and passing to another thread, which makes it really hard for you to, after passing the message, modify somewhere there. Not impossible, just really hard. The fact that everything is done from message passing makes all the inter-thread communication explicit. If you have a shared state somewhere, for example, a struct, and it's hidden behind a mutex, and there is like an integer field in this struct, if your thread locks the mutex and modifies an integer field, it's not really clear what is the intention behind it. How does it affect the other parts of the system? When you're using message passing, usually the message communicates an intent. Something happened, and you would like to inform our threads that, hey, I don't know, an HTTP request has arrived, or some other event happened in my system, and you can basically search for usages of that struct to see how different parts of the system react to it. Moving on with the actor model, I'd like to present an example of a technology which uses it everywhere. So Elfo is a Rust framework that enables the developers to do actor programming. It already has all the necessary building blocks for you to construct a concurrent system using the actor model. It has the message passing, obviously, because there is no actors without messages. It also implements routing. You can decide dynamically where your message goes. It automatically handles actor restarts. If your actor panicked for some reason, it doesn't bring the entire system down. Much similar to Erlang, Elfo is able to restart your actor, and you can define policies on how that happens. Elfo supports the distributed mesh, which we'll be talking about in this talk, and much more. Before we dive into the distributed part of Elfo, let's take a look at the simple example of an actor. So, as I said before, actors are basically concurrent tasks, and that maps nicely to the async tasks in Rust. Here we have a very simple actor which first of all sends a message with the text "Hello World," and then receives the message and checks if it is a reply to his early message. So you can send messages, you can receive messages, and both of these operations are asynchronous. While it is probably obvious why the receive operation is asynchronous, because there might be no messages, so you need to wait for them. The send operation is also asynchronous, and it might sound weird, but we will get into that a bit later in the talk. LFO also builds a couple of powerful abstractions on top of messages, such as requests. So the whole code in the previous slide can be replaced with just a single context.request, where you send the message to some actor and you get a response also in the form of message in yeah, that's a finished sentence. Actors in LFO are organized in groups. You can think of groups as general areas of business logic in your application. For example, you can have a WebSocket actor group where each actor handles some request from a browser, maybe a mobile app or somewhere else. You can also have an aggregator actor group. If you're developing, for example, an advertisement system and you want to aggregate events from your from actors which handle WebSockets, you might have a separate actor which aggregates clicks and a separate actor which aggregates views. So fundamentally, they are doing the same thing, right? They are computing some number statistic, but they are doing it a little bit differently, because one is aggregating one kind of events and another one is aggregating views. Defining messages in LFO is as easy as defining a struct in Rust. You just declare a struct as you would normally do. You can declare any struct which is serializable. There are some cases where you can declare a non-serializable struct. We'll cover it a bit later. But in the simplest case, your struct is serializable. You just define it and add a procedural macro on top, saying that this is a message. If you define a request, the process is completely the same, except that you need to define what message are you waiting in response. So in this example, we have a greeting request, which expects a reply, in reply to the request. Before we continue on this discovery of the distributed mesh, let's take a look at how message passing is performed on single node. So imagine an example where an actor wants to send a message. Which steps does it go through? First of all, the message goes through the so-called group router. As I said before, you can define dynamic rules on where your messages end up. And if you're a WebSocket group, for example, and you want to send a message to your aggregator group, well, the router needs to know that, hey, this kind of message goes to the aggregator group and not somewhere else. Once we have established which group the message belongs to, it's then up to the actor router to decide which actor it goes to. So we are inside a group, for example, an aggregator group, and we decide which actor this message belongs to. It's important to note that all this logic is user-defined. So it is you, as a user of the framework, define which messages go to which groups and which messages go to which actors inside these groups. Finally, once the message passes through the actor router, it goes into the actual mailbox. This might seem familiar to many of you. This is just a Rust channel which contains all the messages. So if you worked with crates like Futures or maybe Crossbeam, channels might be familiar for you. An interesting property of messages in LFO is that sending a message can actually fail. It might not make any sense in the beginning. Like, we're sending a message on a single node. What's there to fail? Memory, like if we are handling memory failures, we are in a big mess. But when you try to send a message, for example, the group router might decide that, hey, this message does not belong anywhere. I do not know which group needs to handle it. In the same way, the actor router might not be able to find an actor this message belongs to. For example, your actor for some reason panicked and was not restarted yet, so there is literally nowhere to send the message to. Finally, the actor's mailbox can be full. We intentionally limit the size of a mailbox because different actors can work at different paces. For example, one actor can produce 100 messages per second, but another actor can handle only 50. This means that if we just allow the first actor to send messages infinitely, we'll just allocate more and more memory to buffer all these messages, and finally we will run out of memory. So we need some kind of a back pressure mechanism from the actor mailbox saying that, hey, that's enough, I have 10,000 messages, I can't handle any more, wait until I will handle my current work. This approach has an advantage. So actors fundamentally need to handle the fact that the message, it is possible for the message not be delivered instantly, for the message delivery to fail. So all actors written in Elfo already handle this case. This is like normal operation. The advantage of that is that you can introduce more cases where the message delivery fails. So usually software goes in the other direction, right? We want to reduce the number of failures, right? But we will take an innovative approach and we will make the number of failures higher by introducing some faulty medium like network. Sending and receiving messages is completely opaque to actors. They do not know how they are delivered, they do not know how they receive a message, they just know that they are somewhere there. So it is up to us to implement the connecting link between the two actors. This means that we can just put two actors on two different nodes. We can implement some kind of a network protocol between them, and for these actors it will seem same as if they were executing on the same node. Well, that's of course given the fact that your network protocol is not buggy. Of course, everything every sentence which starts with just is a lie, so there is actually a list of requirements we need to go through before this would actually work. First of all, we need to handle the message passing and routing. Once again, message passing is core to Elfo, so it needs to work reliably, and we need to support the routing logic between actors on different nodes. We also want the flow control, which is the alternative of the mechanism of limiting the actor mailbox size. We don't want the situation where an actor on one node sends a lot of messages, which the actor on the other node cannot handle. We want to somehow limit this stream of messages from the other node to avoid network congestion. We also want to, if possible, compress the messages, because it might be possible that the two actors are in completely different regions and the network latency between them is really high. This means that we want to pack as much data as possible into the batch of bytes we send them. Finally, we want the system to be observable. If we are introducing more failures to the system, we want to be able to debug it. We want to have metrics, we want to have tracing, we want to provide all the tools for the developer to actually work and debug the system. At this point, you might ask, why not gRPC? gRPC implements a lot of things on this list. The main reason why my company at the time did not choose gRPC is these three. So first of all, we did not want to have any compatibility layer between Rust and gRPC. With gRPC, you define all the protocol in protobufs, and you generate the Rust code from these protobufs. So if you have some struct inside your application, it will need to be somehow converted into these protobufs to work, to be actually sent over the network. We also do not like the gRPC's type system, well, more like protobufs type system, which is not as expressive in Rust. Again, there is an extra friction in converting an enum or converting an enum from Rust into the gRPC, which we wanted to avoid. And finally, we believe that we will be able to provide a more efficient serialization than gRPC, more efficient in terms of the speed of compression and decompression. Protobuf is actually a very hungry protocol for CPU. It was developed under the assumptions that network is very expensive and the CPU is very cheap. Well, while that might be true for Google, that's not true for most of the companies. We decided that the best approach to represent actors would be a network mesh. A network mesh is a simple thing where you have a cluster of nodes and each node is connected with all other nodes in the system. So here we have a cluster of just 3 nodes and each node is connected to all others. For this to work, we need two pieces. We need two pieces of logic. So first one is service discovery, and the second one is the actual connection between the nodes. Service discovery in LFO right now is implemented in a very simple way. You just list all the nodes which are in your cluster, and the server will automatically try to connect to all of them. This list can be changed dynamically. For example, if you manage your configs using console or something like that, you can change the config on the fly, send an appropriate signal to LFO, and it will try to connect to the new nodes you have added. LFO supports not only TCP, but also UDS, which is faster protocol available on when both of your services are on a single node, which is very convenient when your cluster is deployed in Kubernetes and you have two services which are physical on the same node but logically separate. To establish a connection between two nodes, we built two TCP sockets. I will call them TCP sockets for the ease of use, but bear in mind that it is completely possible to use UDS instead. So we established two connections. First one is control, and the second one is data. Control is mainly for the nodes to greet each other, to exchange what versions of the protocol they're using, what capabilities are there, can the node support, what kind of compression algorithms does the other node support, and which of the nodes will establish data connection. The data connection is actually like the meat of the topic. It's the connection we use to send all the messages and flow control data. So control is the low bandwidth with meta information, and the data is a connection which is very high bandwidth, which sends all the messages. In practice, however, we don't just keep one data connection per a pair of nodes. So you have one control connection between two nodes, but you have multiple data lanes associated with them. This is because each pair of actor groups, more like, have a separate data connection. This is again to avoid a very noisy actors from just congesting the data connection and to separate them not only logically but physically as well. So the data connection itself is a relatively simple thing. It has its wire format consists of two parts. First of all, we have a very simple format to encode message headers. These are things like what is the type of message? Is it a regular message? Is it a request? Is it a response? What is it? The length of the payload, the name of the message, and metadata like that. The actual message is encoded in message pack, which is not the most optimal format for this type of application because it is self-describing. So when you're looking at message pack, it's sort of like JSON. You have all the field names, and you can, without even having the description of your protocol, you can sort of devise you can parse parse the message from message pack. So we will talk about it later, how we can optimize it further. And finally, we do apply optional compression if it is enabled on data connection. Speaking about compression a little bit more, first of all, we did not use gzip. Gzip as a family of algorithms is older than me by 7 years. We really should stop using it as a default in the industry. There is almost always a better choice out there. And for us, this better choice was between LZ4 and ZSTD. For those who are not familiar, LZ4 provides a slightly worse compression rate than ZSTD, but at the same time, LZ4 is slightly faster at compressing and decompressing data. Since we are very latency sensitive, we decided to go with the LZ4, not ZSTD. So basically, a rule of thumb for us was that everything at rest is ZSTD, everything in flight is LZ4. The way the compression is implemented is that we buffer messages until some condition was met. If we just take a single message and we compress it with LZ4, we won't get much of a compression ratio. The algorithm needs more data to work efficiently. So we accumulate messages in the message batch for some time, then we compress the whole thing with LZ4 and send it as one big blob of data over the wire. The problem with this approach is that anytime you spend actually accumulating the messages in your message batch is an added latency to these messages. So, for example, the message A was added the first here in the batch. Then when we have waited a little bit to add message B, message C, and maybe some more, we have improved the compression ratio, but all this time message A is waiting to be sent. So we have extended the latency of message A. We need to be really careful about that. LFO does some very basic heuristics based on the message size to decide whenever to send it or not. And in the future, we plan to implement more sophisticated algorithms to decide to balance the compression ratio and latency. Finally, let's get back to the problem of actors which can be overwhelmed. So here we have two nodes. And actor A on the first node is sending a lot of messages to actor B. Same as we had on a single node, if we just let this stand, the actor B will need to accumulate more and more messages. And this doesn't really make sense, because the processing power of actor B is for some reason much lower than the rate with which actor A actually sends the messages. So they will be piling up, accumulating, spending our memory, and most importantly, congesting our data connection, not allowing any other messages to come through. To fix that, we have taken an inspiration from the TCP, because we are basically implementing a network protocol on top of TCP, so might as well steal from the best. And we have implemented the flow control using Windows. So a basic idea is that a window is number of messages an actor A can send without waiting for an acknowledgement from actor B. This means that, let's take a look at the example. If actor A sends 100 messages, and this means that the window of actor B is 0. It has spent all its budget for sending messages. After that, nothing happens. The actor A needs to wait until the actor B says that, hey, I have indeed processed all 100 messages that you sent before. Only then actor A can proceed, because otherwise, again, it will just send more and more data without actor B actually being able to process it. Once the actor B has sent an acknowledgement that, hey, yes, I indeed processed all the messages, the actor A can proceed with sending more, because their window has restored from 0 to 100. One of the things we do is that we monitor the speed with which the actor B is processing the messages. So if for some reason your system is overloaded and the processing power of actor B comes from 50 messages per second into 25 messages per second, this means that we need to update the window. We need to make sure that the actor A knows that, hey, the actor on the other side is really struggling. You need to send less of data, and we handle that by sending the appropriate window updates. Finally, this whole thing needs to be observable. Like we have introduced network into the play, which is famous to fail, and it's the truth of the reality we live in. Like we need to handle faulty network, and we need to be able to debug it. LFO tackles this problem from multiple perspectives. So first of all, LFO, even without having any network in play, provides you with so-called message dumps. Basically, you can flip a flag in a config, and the LFO will dump all the messages in the system, everything that has been sent, everything that has been received, everything will be in this log. There are two options. You can dump it in the file, like I did, or you can dump it into some kind of an analytical database and run some interactive queries there. What this allows you to is to very quickly see how the system thinks. So when debugging the code, you already have access to your code, right? It's like in your editor, but you don't have the input data. And this message dump basically allows you to have this input data. You see exactly what is coming inside your actor, and from that, what kind of branches does it take, which really speeds up the debugging. LFO also has tracing. You might be familiar with tracing from OpenTelemetry. LFO understands tracing in a little bit different way. So trace ID is something that sticks to everything once you attach it. When you are handling an HTTP request, for example, you create a trace ID, and any events which you send from this actor while handling this request, you attach a trace ID to them. As soon as that happens, all the logs, all other messages which are generated by other actors while handling this message, all will have this attached trace ID with them. It means that you have a method to see everything which happens in your system which relates to a particular request or a particular operation. For example, your user might come to you and say that, hey, your server has returned HTTP 500 to me. Debug this error. If they provide a trace ID, you can go into the message dump. You can go into the logs and query by trace ID, and you will see all the messages which have been sent while handling this request. And of course, Elfo provides a lot of metrics. For the single node use case, Elfo has already all the metrics you need to debug a local issue. This panel is only for one actor group, so you have the message rates, which are also splittable by the kind of message you are sending. You have the CPU usage, of course. You have the allocation rates and much more. One of the most important metrics here is message waiting time. The system tracks how much time does the message spend in the actor's mailbox waiting to be handled. When you deploy Elfo with the use of the network feature, you get even more metrics which tell you about the volume of traffic between different groups, between different actor groups. It tells you how the flow control reacts to the system load. It tells you how much, what are the window sizes of different actors, and again, much more. So you have a complete picture if there is an incident to debug and see what exactly went wrong. Finally, with some effort, you can build a picture of what a mesh looks like in your case. So you can derive from message dumps and from other metrics the structure of your cluster and see it in real time, seeing how many requests are being sent between different nodes. In this example, if you a bit zoom in, I'm not sure if it's visible on the back, but each edge on this mesh has the number of requests being sent. As an end result, we have an actor system which seamlessly mapped into the distributed network mesh. We have actors which have 0 to very little code changes now running on completely different nodes. None of this would be, of course, possible without the Rust ecosystem, because the main reason why this all works and why the developer experience is so good is because we have used the hell out of Rust macros, which are extremely expressive. We are privileged to have a native async support, which works really well. And of course, the Elfo is not Tokyo specific, like we want to support other runtimes as well. But Tokyo is what we have used in production, and we enjoy not thinking about async runtimes too much. What are the next steps for Elfo? So, as I said before, we can and will do a better serialization than gRPC. For that to work, we need to switch from message pack to some format which does not describe the schema, which is, well, that's not the correct way to say it, which is not self-describing. So again, message pack is self-describing because it has all the structure encoded, all the fields. You can deserialize it without having a schema. We don't really need that if both nodes speak the same protocol. Both nodes have the same definitions, have the same Rust struct definitions, so they already have what the data looks like. We can do this with using crates like Postcard RS, which provide us exactly with that. They provide us with the non-self-describing format, which works really well if both ends of your connections know about the schema of your data. Expanding on the Kubernetes use case with the two services being physically on the same node, we want to support shared memory for communication as well. UDS is fine as all, but in our limited experiments, we were able to get a better throughput and latency from using the shared memory for communication instead of UDS. We want to be able, now that we're talking about the distributed system, we want to be able to think about parts of the system without specifying individual actors. So, for example, if you have a set of actors which handle, what would be an appropriate example? If you have a set of networks which handle connections to database, for example, or connections to some external service, I do not want to select an individual actor in this group. I want to select the actor which has the best latency right now. So I basically want to be able to send a message and say that, hey, I want this message to be handled by an actor with tag ClickHouse, for example, and select the one which has the best latency right now. So that dynamically balances your system. If some parts of it are overloaded, you will just go to the ones which aren't. We want to provide more mechanisms on top of messages. So you already have seen requests. We also want to provide subscriptions, which are a bit tricky to implement in the when your communication medium is faulty. But that's something we believe that this is a powerful pattern for developers to use. You can subscribe to updates from some actor or from a database or from something else and get all the updates in the form of messages, which is really useful. And finally, we want to support other runtimes. Again, we really enjoyed working with Tokyo, but we understand that this might not be the best solution for all. So we want to support other runtimes like Mini.io and stuff like that. Thank you very much.
Questions?
Hi there. So we've got two questions. The first one's pretty quick. What's the MSG macro that you had for the pattern match near the start?
Sorry, come again?
The MSG macro.
Yeah, message. So that's a very good question. Good catch. So the message macro, let me just quickly, I think it will be more visual if I actually show it on the slide. Bear with me. Yeah, here it is. So you can see that the message macro accepts a match statement, and it transforms it into a bunch of if statements, because you cannot actually match an envelope against a struct, because an envelope is like this opaque type which you can cast to some specific types. So we transform the match statement into I believe it is something like envelope is, and then we pass it hello as a generic. We don't want the user to actually write that. Match statement is much more friendly, so we built a simple macro to handle it.
Awesome. The second question is, can the mesh be kept alive indefinitely? How do you deal with versioning?
Again, a fantastic question. So we follow certain rules in terms of protocol evolution. So obviously, if you just delete a field and deploy a service, well, it won't work because some other service might expect this field to be present. So we do soft protocol evolution, meaning that we first add another field, and only once all the consumers are switched to the new field, we delete the old one. But we also want in the future to check that mechanically. We want the system to be able to tell us that, hey, you cannot deploy this service because it contains a breaking change and your cluster might go down. So it is possible to check that statically because we have all the message definitions, and we will do that in the future releases.
Fantastic.
How do you know which messages are valid for which actors? Is there some way that you can determine that statically, or do you have to how many match branches do you end up with in practice?
Right. So when you define a service in L4, you define first of all topology. You list all the actor groups which are available, and you start with defining group routers. So you literally specify a lambda which says that, hey, if it is a message of type hello, it goes to this actor group. If this is a message of type goodbye, it goes to different actor group. And then on the actor level as well, you define again a router with a lambda which makes a decision which actor this goes to. Does it answer your question?
Hi, thanks for the talk. It was really good, especially given how little time you had to prepare. It was really good. I think there's probably quite a lot of overlap with what we work on, because we also work in distributed computing. So how do you test this? And that's somewhat of a loaded question, so I understand you might not have a lot of time to answer that, but these big distributed systems, what kind of technology are you creating to test this?
Right. So for testing, well, there are really two things. So we can leverage the fact that the actors literally do not know where they send the message to. So we can build a testing harness, and we already did, which basically says that, hey, I will start an actor, and I will behave like the rest of the system. So I will send the message into the actor, I'll get some response, and I can assert some stuff on top of that. So that's how you test an individual parts of the system. For the system as a whole, it's a bit more complex topic. You need to have some kind of integration tests, which is a bit out of Alpha scope, but something that we are thinking about. So we do have ways to do unit testing. The integration testing, especially in the presence, we want some testing in the presence of like network failures, like how do actors behave if the message cannot be delivered. This is some stuff we are exploring now. Yeah.
Thank you for a great talk. And I'd like to ask a question about the, for gRPC, for example, there are like a re-implementation that people call like a buff IO. So they have the service that manage the schema for the schema evolution, for example. And when I was at Bloomberg, they also have a service like a pass service. Also have the centralized place when you can publish your schema and do this like service discovery and routing. Like, do you intend to build the same? Because it have the semantic versioning of your services, and it make a lot easier to client and server that can communicate if even they fall back certain like patch or minor version, they still can communicate, for example.
Yeah, Buff.io is actually really cool because it provides you with some CI for gRPCs to say that, hey, your change is actually a breaking change, it will break your clients. We want something like that in practice. So like answering like the first part of your question, how do we manage with protocol? It's usually a separate crate. So there's like a separate crate with all the structs possible to interact with different services. As I said before, we do want something like Buff.io. We want to be able to statically tell the user that, hey, if you're going to deploy this service right now, there will be a breaking change, everything will be destroyed. So like we resonate with what Buff.io does. I think this is like the direction we might move into. Yeah. Does it answer your question? There are a couple of questions here on the right.
Hi, thanks for the talk. Are there any plans to add persistence? Because one of the patterns where I've been using actors in the past is it's really powerful to be able to, assign like at least some of the actors persistent state, so that when you do restart them, they at least have an idea of how they can kind of rehydrate themselves and bring themselves up to a good state.
So you said any plans for
persistence?
Persistence. So in production, we actually have some form of persistence. Actors have state. The way it is implemented is that we have a separate actor, which is, it's called state manager, so to say. You send a message with all your state to this actor, and it will make sure that it is persisted to disk. You can get state from this actor by asking that, hey, I'm actor 1, 2, 3, 4, 5. Get me the most recent state. So it is useful in general sense. We do, however, we did try to limit the number of actors which actually have state, because it does impact your ability to restart them easily. So the easier it is to bring the actor back online from a died state, the more resilient your system is.
So does Elfo handle load balancing of actors, or does it rely on the underlying operating system to kind of balance their work across the system?
You mean like between different CPUs and stuff like that?
CPUs or nodes in the mesh, across the whole width.
Right. So first of all, you statically define which nodes have which actors. So like there's no way to balance actors between different nodes, because there is like always set places where actors appear, so to say. Between different CPUs, though, that's for sure. Like we do provide a functionality for you to pin certain actors to different CPU cores. For example, if some of your actors are real time and you want them to have exclusive access to like 6 CPUs, you can do that, and you can map all the rest of them to the rest 8 CPUs or something like that.
One more question, Megan. Last minute one.
So this looks like a pretty impressive framework, and it sounds like it's in production. I'm wondering, what do you use this for at the moment?
Right. I'm not at liberty to say a lot, so I worked for a high-frequency trading company, and this technology originates from there. It is used for all the services in this company, and it is indeed used in production. So, like, we do not advise the LFO to be used in production right now. We have a version coming 0.2 from which we will encourage people to use it. So, like, before jumping into actually using the LFO, just wait a little bit. But it is used in production and for a couple of years. Yeah.
Thank you.
Not a technical question, but is there a fun story behind the name?
I don't know. I don't know, actually. Unfortunately, I joined the team when the name was already set. I wish I asked the original author about it, but yeah, I mean, the LFO is obviously from the Disenchantment series, but I don't know much more than that, sorry.
In the presentation, you mentioned that it can manage any HDD issues or network issues. Did you use any, I don't know, chaos testing to test these issues, or?
I mean, we do want to use to integrate like the network for faulty network testing into the CI. It's not the case right now. The way we have rolled out the system in production was that we had a pretty good pre-production environment, which is like very similar to production. So the way it was tested basically was that we will roll out to pre-production. DevOps will scream at us, we'll roll it back, fix stuff, and repeat. But we do want to introduce a more rigid testing about network, about the faulty network. It's something on our to-do list.
Second question, possible. Did you compare to the resource or any other network requirement between LFO and any other system, for example, Apache Kafka? Okay, the Apache Kafka is not mesh-based, but can be used to the shared version as well. So in this case, we can simulate with this similar system.
Mm-hmm. I think a more fair comparison would be to a library called Akka. So I'm not sure if I'm pronouncing it correctly, but Akka is a Java library which, first of all, kind of was an inspiration to LFO, kind of wasn't. So we do want to compare LFO maybe against some actor systems, but again, we first want the technology to be sound and to reach 0.2 release, which will be like the more public release, but it's definitely something which we probably should do. I mean, comparing with our systems. Yeah.
How do you deal with CPU bound work? So if you do something that's completely expensive in a task?
Yeah, that's a really good question. So for context, Tokyo is like I/O optimized, so it handles well. And how would I say it? So the Tokyo is a runtime for cases when you have lots of I/O and not a lot of CPU bound work. So the question is completely valid. We did have a separate thread pool for CPU intensive tasks, which was managed by Ryan. So we basically used a different, well, not runtime exactly, with different separate thread pool for CPU intensive tasks.
Makes sense.
Thanks for the talk. Please give a final round of applause for